Well, again, welcome everyone, and thank you for your interest in this workshop on networking topics. This is a workshop that is organized by the New York State Education and Research Network, NYSERNET, Engagement and Performance Operations Center, and the University of New Mexico. My name is Jorge Cuchigno. I'm one of the organizers, but I certainly would like to recognize my co-organizers, and we are a team of organizers. I will let them to speak briefly shortly. I want to start with a brief overview of what this workshop will be. From UofSC, I want to thank the National Science Foundation because they certainly help us develop some of the material that you will be using in this workshop. So we have a two-day workshop. The first day is today from 10 a.m. to 2 p.m. Eastern time. So we have several presentations. We will start with the perfSONAR, and then we will have a hands-on session on perfSONAR. Then we'll have a break. And certainly we also have something new that we're implementing, breakout rooms. We'll have rooms where we will have people talking about perfSONAR, data mobility, science DMZ, BGP, network security, and P4 programmable switches. So you can choose, and if you want to move from one room to another, that's something that you can do as well. Day number 2, we will have BGP, 2 sessions on BGP, and then the breakout rooms and network security. At this point, I want to let the co-organizers, I want to let them introduce themselves. So Jason, do you want to go from here?
Sure, and thanks, Jorge, and thanks everybody for taking the time to join us today. We were shocked and amazed at this community of just how much interest there was in this workshop. Over 400 people signed up, and I think even more after we stopped watching the numbers as closely as we did. So it's really evidence that this training is still necessary and valuable for everybody. And while we can't all be in person quite yet, we're excited to have everybody here and be able to share some of these valuable lessons in CI infrastructure. And we hope that people get something out of this. Everything will be recorded, all the materials will be shared. And as Jorge mentioned, the breakouts will be an opportunity that if you just have questions and want to come in and talk about any of those topics, we have some experts that'll be available. So thanks again to everybody for joining, and hope you get a lot out of this experience.
Thank you, Jason. And we do have to recognize the team from NYSERNET. I don't know if Jeff is here, or Christy, do you wanna talk about NYSERNET?
Sure, thank you, Jorge, and thank you, Jason, and all of the other folks at EPOC and University of South Carolina, and all of the other presenters and speakers. Just want to welcome all of the participants. As was mentioned, it was an incredible response to this, so hope everyone enjoys the presentations and gets lots of good information out of it. And we will see you in the breakout rooms, and enjoy the day.
Thank you, Jeff. Well, I want to also, again, mention all this information is in the website. I will share my screen and I will put in the chat window as well. So all the presentations, if you scroll down, I'll copy these and I will put in the chat window the URL of the workshop website. The presentations are online, and you should have received an email with the instruction on how to enroll, register and enroll to have access to the hands-on sessions. However, if you didn't do yet, for each hands-on session, there is a URL that will lead you to the registration of the platform, and access to the material. The presentations, all of them will be online. Some of them are already there. Information about the breakout rooms are also at the bottom. With this, I would let Jason lead the next session. Jason, I will, if you want to take from here.
Yeah, I will be introducing our first speaker. And as we discussed, the first topic of today is going to be perfSONAR. So I'm pleased to be able to introduce a member of Indiana University and EPOC who's going to be presenting this. Doug Southworth works as a network systems analyst at IU, and his area of focus right now is on performance measurement tools, perfSONAR, NetSage, and a couple of other areas of focus that he's been talking about. So he's a great resource and a great presenter that's going to be able to talk to some of these tools to hopefully get people started and interested and excited a little bit about the topic of network measurement. Before he was at Indiana, he worked with a couple of other agencies, including the United States court system. So we do welcome Doug and hope that he'll be able to explain a little bit about perfSONAR before we get into the hands-on section a little bit later today. So Doug, if you're ready, share your screen and please get started.
Well, thanks again, Jason. Appreciate you giving me the kind introduction there. And yeah, we're going to talk a little bit today about kind of a specific section of perfSONAR. This will be a little bit less of a general overview and more of a introduction to specific being able to use nodes to test from one node to another and do some troubleshooting. So I'll talk in general terms real quick about what perfSONAR is, but we're going to dive into a slightly deeper topic today. So if you're wondering why I brought you, that's what we're going to look at. Some methods and motivations for why having a node in your network is going to be valuable, not just to you, but to the community as a whole. So one of the things that I tend to see when people stand up a perfSONAR node, and let me stop right there for a brief second. For those of you who may not be familiar with what perfSONAR is, it's a measurement and monitoring suite. It's a collection of open source tools that is bound together all in one package. And we're going to talk about how that works briefly in the next couple slides. One of the things that it does is regular testing for either bandwidth or latency or routing. There's a number of automated regular tests that it can do. But one of the issues that we see with perfSONAR is people will stand a perfSONAR node up, they'll have it in their network, they'll start that regular testing, and then the node just kind of languishes. It starts to gather dust, as we say, and typically that means they also start to get out of date. Regular updates aren't being done. And when that kind of things happens, it actually is almost worse than not having a perfSONAR node at all in your network if it just continues to languish. And so really what I want to look at today is how to make perfSONAR a useful tool in your day-to-day operations when you're doing network management, when you're doing network troubleshooting. There's a lot more to it than just regular testing that maybe you go back to every 6 months or every year and take a look at how your network is performing. Because RNE networks, they're constantly in flux. They're constantly changing. They aren't really self-sufficient. There's a lot of things to be aware of, and performance that was good just a couple of weeks ago may be suffering now, or you were pretty sure you knew the route from your institution to another institution, what path that data was taking, but maybe that has changed now without you even realizing it. So perfSONAR gives you eyes to see what's going on outside of your borders, and I mean, internal to your network and external to your network. So being able to have a perfSONAR node and have it maintained and keep it in that useful state in your network is really, really crucial. And so that's kind of my pitch. So what do I want from you? I want you to put up a perfSONAR node if you don't already have one, but even more than that, I want you to maintain it and use it as a day-to-day resource if at all possible. The other part of perfSONAR is, as you're going to see in this presentation, it's not just for you to have eyes beyond your borders, but it works with the entire global RNE infrastructure. A lot of my job is based around finding performance problems in networks that I don't even administrate or manage, but I'm able to see those problems because Institution A and Institution B both have perfSONAR nodes. I can run tests to those. I can run tests of them from my institution, from any other open and accessible perfSONAR node around the globe. I now have insight into what is going on between those two networks and the networks that are in between those networks. Because if you're on the East Coast and the other side is on the West Coast, you're traversing a bunch of different topology and a bunch of different networks that you don't control. But with perfSONAR nodes scattered all across that path, you can start to figure out what is going on in that network. So it's not just for you, it actually helps out the entire global R&E community. So with that, my pitch is over, and we'll start looking at some actual commands and syntax. So pScheduler is the piece that really makes this entire thing tick. So a lot of you may have used iPerf before, one of the variations of it to do bandwidth testing, or you've used traceroute, or you've used ping to check latency or round trip times or that sort of thing. perfSONAR incorporates pScheduler that makes that kind of stuff work between two different perfSONAR nodes. Because if you're running an iPerf test for bandwidth, you want to know that that bandwidth test is exclusive. Because if you're doing 3 iPerf tests at the same time to 3 different institutions, you're not going to get a true picture of what your bandwidth looks like. So pScheduler makes sure that when you schedule a test, that the test is exclusive, that there's only one happening at any given time. And it also makes sure that there's access control during those tests, that you're only testing to institutions that you want to allow to test to you. If you have some security concerns and want to bring that testing back to just a few specific regional partners or maybe even international partners. But all those kind of things come in with pScheduler, where it does all that coordinating for you. It does all of that security for you. So unlike with a iPerf test, where you actually have to call somebody up on the other end and say, hey, I want to run iPerf, could you set up an iPerf instance that's listening for this test? And then when it's done, can you shut it back off again? You don't have to do any of that. It's all automated. You can run it from your end. So the basic syntax is fairly straightforward. It's just pScheduler, pick the task you want to do, the test type you want to do, and then throw some options on the back of it. And the reason for this is there's several different tests that can be run for any one particular type of test. For instance, you've got a bunch of different options for running bandwidth tests. You've got different options for running routing and trace routes, that kind of stuff. The -- help tag is absolutely your friend. So if you want to know what kind of tests are available, you can do a pScheduler task -- help. And now you're going to see all the tests that are available. And once you pick a test, if you don't know those options, you can now run the -- help after you've picked a specific task you want to do. And now you can see the specific test options that are there, because there's a lot in there. There's a lot to dig into. So if you ever get stuck, if you ever get trapped, you can't figure out the syntax, it's all right there in the manual pages. You don't have to go Google it. It's right there. So the remote commands are where we're going to spend a lot of time today. So the source and destination flags do exactly what you would think they would do. If you had source to a test, or you had destination to a test, then they're going to run the test to and from those locations. But the interesting part here is that you do not have to, your specific perfSONAR node doesn't have to be the source or the destination. We can run any one of these tests from a first node we don't own to a second node that we don't own from our specific node. And that's where the real power comes in. That's where being able to have insight into networks that we can't touch, but start to make inferences about performance problems comes into play. That includes all the diagnostic tools that perfSONAR has on board, and even some of the scheduling tools, in terms of if you run a test and it's the other node comes back and says, well, I don't have time to run that test. You can even look at the scheduling piece and see if that node is just busy right now, or if that node maybe is completely oversubscribed and too busy to do anything. All of those are options that you can run against other nodes from your node. So for instance, this is a box. This one right here is actually at Indiana University. And I ran a throughput test from, we have a node in New York and we have another node in Seattle. And so you can see I ran a throughput test with the New York node as the source, with the destination being the Seattle node. And cross country, I'm getting almost 10 gigs. That basically is as good as that is ever going to look on a 10 gig circuit. But I ran those between two nodes that I wasn't logged into. perfSONAR, again, gives you the ability to run these kind of tests and have this kind of insight through this global already infrastructure of nodes to see what's going on outside of your borders. Same thing, take a look at something like trace path. So again, from New York to Seattle, and this isn't a trace route. Here I specified a tool I want to run a trace path. Why? Because I want to see the MTU at each individual hop and see if there's any changes. I know I'm starting at 9,000, but do I end up at 9,000 on the other end? So while a trace route just gives you, here's the hops, the trace path does a little more work and lets you know what the MTU size is from end to end. So by specifying a tool there, I can use a different tool than the standard trace route. So I did mention briefly built-in diagnostics. So if you have a perfSONAR node and you're having issues with maybe testing, you get errors that the test wasn't scheduled successfully, or that the node on the other end was not responding, or something along those lines, you can actually do some troubleshooting on your own without even calling the owner of the other node to say, hey, something's wrong. I may be on your end, I'm not sure. If you just run pScheduler troubleshoot, it'll run through a series of basic tasks on your node locally. You can specify a remote node, and what it will do is run the test on your node first, and then on the other remote node secondly, and then it'll run tests between the two nodes to see if there's a problem communication-wise between the two. And then we've been talking about these remote commands, running commands on two nodes that aren't even on your network. You can do that with the diagnostics as well. The syntax is a little bit different. You have to specify a host first, but you can specify a host that is on someone else's network and then a remote node on the other side. And you can run all these pScheduler troubleshoot commands and see what the performance is like briefly, and also just things like NTP, are the clocks in sync? Because a lot of these tests require that the clocks are actually synced up. So this will run through all those permutations and see if everything is ready to go. So you'll get something that looks like this. Again, I specified our New York and Seattle nodes. So this is actually running all the diagnostics, again, between two hosts, neither one of which I'm logged into locally. So you can see it goes through, it checks for MTU, it checks to make sure that the pScheduler service is actually running, checks the API levels, checking the clock, just making sure that NTP is up and going. So it runs through all of these, and if everything is successful, if everything looks good, you should get this, it appears to be functioning normally, which means you should be able to run a test between any two nodes. But having this kind of information and seeing if and when there's a failure can be really useful when you go to, let's say, the administrator of a node who they don't know they have a problem, but you're trying to test to them and you're coming up with something. You can show them these diagnostics and say, I think the problem's on your end. Here's what I got from the diagnostics. And sometimes that helps narrow down where the problem specifically lives. Also works on pScheduler monitor. So this is one of the things we talked about scheduling. You can see this host rate here is fairly busy, not completely overloaded. These latency tests don't take a lot of time to do, but you can see there's quite a few throughput tests in the stack as well. But this actually shows you what the specific schedule looks like coming up for a host. So if you run pScheduler monitor with no arguments, that shows you what your local host looks like. But in this case, I was taking a peek at the scheduling for our Seattle node. And this just happens to give me some insight into what that box is up to, who its testing partners are, and gives me an idea of how busy that specific thing is. This pScheduler plot schedule is an even more in-depth look at that, because this shows you kind of a window of what's coming up and what's past. And if there's been any failures, they'll be highlighted in red. The pScheduler plot actually gives you kind of a calendar view. It generates a file you can save as either a PNG or a JPEG. And it actually lets you see specific calendar slots to see how busy a specific node is, if it's doing too much work, if it's got a lot of open time. But that's useful when, again, you're trying to test to a node and you keep getting these errors that a test wasn't started or that a test didn't complete. Plotting that schedule can sometimes give you some insight into how busy that node is, how many tests it's trying to run in a given amount of time, and maybe it literally just is oversubscribed and doesn't have time for you to run tests against it. And sometimes it's nice just to be able to reach out to another node administrator and say, look, you may not even realize this, but you've got a lot going on here. You may want to take a look and address how often people are testing to you. Okay, so that was a lot. I know I just drinking from the fire hose, but let's take a look at how this would actually be used in some real world scenarios that we've come across with EPOC. Initial performance was not good on a specific circuit. Somebody reached out to us and said, hey, we're trying to get data between these two endpoints and it just isn't working. Can you help us figure out what's going on? So there's a lot of acronyms in this one, but it's the National Radio Astronomy Observatory, which is part of University of Virginia's campus. They kind of hang off to the side of that, but they do at one point go through the UVA campus network, and then the South African Radio Astronomy Observatory. So we're talking about a fair amount of distance to get over to South Africa. And they're trying to transfer some decent sized files, but they're getting really abysmal performance, less than 5 meg on average. So we started taking a look, and using perfSONAR, we were able to run a few trace routes just to see what path that data was taking, because we had a perfSONAR node that was right next to the SARAO, and we had a couple perfSONAR nodes at NRAO and at UVA. So we were able to see which path the data was taking. So what we found out was that initially there was some asymmetry there. Data was going out one direction, coming back another, and it was kind of taking a circuitous route that wasn't really the most efficient. So we started there using perfSONAR, that trace route information, took a look. We made some route corrections, but it honestly didn't change the performance at all. So now we got to dig a little bit deeper. So we start by testing with bandwidth, going from a couple different nodes in a couple different spots, Internet 2 in Washington, DC to all the way to South Africa, essentially the SARAO, we were getting reasonable performance. Checking from Atlanta to Internet 2 in Albany, because when we made the route correction, instead of coming across a northerly route, it was coming now basically from Africa to South America up through Miami and then going, up through Atlanta and up towards New York, Washington, DC. So we checked that last hop just out of curiosity from Atlanta to Albany. We're getting great bandwidth across there. But now that node that we had good bandwidth from South Africa to Washington, from Washington to NRAO, which is they're right next door, we're getting poor bandwidth, lots of retries. Same thing to the HPC at UVA, lots of retries. Now we're even taking a look at NRAO to the HPC center at UVA. They're on the same network, and we're getting a lot of retries. So the problem seems to be somewhere deep in their network. So we asked the network engineer for just kind of a block diagram. What does your network look like in general? So Maria up here is the local REN that is giving them connectivity. So from there, it jumps through a series of gear. This side is more the UVA network. And then at this point, about 3 hops in, that's where we get a 2x10 link that runs over to NRAO, and that's where they join into the UVA network. We know for a fact that the NRAO node is set up to a MTU of 9,000. We know the Maria router is actually set there as well. The campus, though, for UVA is 1,500, but we don't know where that change is made. We don't know if that starts here. We don't know if that starts all the way down here. We've got a little investigation to do to figure out where exactly this MTU change happens. And anytime there's an MTU change, there's a potential for performance problems if that's not done correctly. So we're going to take a quick side trip and talk about path MTU discovery. So what this is a layer 3 construct that allows for one endpoint to figure out the MTU of another endpoint. So if you have different MTUs, if this one's 9,000 and the far endpoint is 1,500, all's not lost. This negotiation can happen as long as PMTD is intact and working end to end. They can negotiate an appropriate MTU and everything works just fine. There's nothing wrong with an MTU change as long as it's done correctly. So if you're 9,000 on one end and 1,500 on the end, and this is working, the two hosts will negotiate. The one that's at 1,500 says, I can't handle a packet that size, but we can break it into smaller pieces, and I can nibble at those 1,500 pieces and be just fine. You lose a little bit of performance, and the longer the distance of the transfer, the more performance you're going to lose doing that, but it still in general will work. You won't get retries, you won't get terrible bandwidth. So, but the thing is, this is a layer 3 construct. So this has to happen at a routed hop. You can't have two layer 2 devices with different MTUs facing each other and expect this to work. It will break. So you have to have one router and another router, one hop apart, talking to each other so that they know how to negotiate this. So very, very brief overview, but basically there is a mechanism that if everything is set up right, that can cope with this. So here's a prime example of that. We take a good working, known good ESNet host. I believe this one was up in New York, might have been in Washington, DC. And we're going to start working our way inward to UVA. We know the ESNet one is at 9,000 MTU. We know that the UVA one is 1,500 because their network is. And these two hosts right up front, they quickly negotiate 1,500. And you can see there's good bandwidth between them. There's a few retransmits initially, but that's kind of the TCP ramp up. But after they figure it out, they negotiate cleanly. There's no retransmits. Bandwidth is solid between the two. So that's ideally what good path MTU discovery should look like. Two hosts able to talk, figure out what they need to do, and transmit data cleanly. On the flip side, we have a host at NRAO that's saying, hey, I'm 9,000. The ESNet host is saying, hey, I'm 9,000. So they start trying to talk at 9,000 with a 1,500 byte MTU in the middle in UVA somewhere. So the first couple tests here, lots of retransmits, and you'll see there's no bandwidth. That's because they weren't actually talking. That means the packets were not making it from A to B. perfSONAR is smart enough to recognize that situation and adjust on the fly. But obviously somewhere in between these two hosts, path MTU discovery is not happening because otherwise you wouldn't see this behavior. You'd see testing start like we did in the previous slide. So now we've got a situation where perfSONAR was smart enough to renegotiate, but not every network tool out there knows how to do that. And you can see the performance is terrible. If we let this go longer, did a 30-second test, this TCP window would keep scaling and the performance would get better. But in general, this is not the kind of situation you want to see when you're trying to do a transfer between hosts. So now we got to figure out where this breakdown is happening. So again, we're still using our remote hosts, one at ESNet, one at UVA. We do a basic trace route, and we end up seeing that somewhere in here is the handoff from Maria to UVA. You can see this is actually the UVA edge router here. So this hop 8 to 9, that's one you want to keep in mind when we look at the next couple slides. So after a trace route, we do a trace path, right? Because we want to now see where the MTU changes. But as soon as we run a trace path, all of a sudden, we disappear at hop 9. Now, this is kind of odd because our trace route made it all the way. So now we had a bit of a conundrum. We actually had to do a little bit of digging into protocols at this point to figure out what had happened. And what we came up with was this. Trace route uses very, very small UDP packets. So they were able to make it through under that 1,500 MTU that was somewhere in the middle of the UVA network. Trace path uses much, much larger 64K packets. And so they were getting stopped somewhere because we had a communication problem. Remember, when we looked up here and did 9,000, they couldn't make it through. So these 64K packets weren't making it through either. So now what do? How do we figure out where the breakdown is? Well, using trace path, you can actually specify the size of the packets that you're sending. 64K is the default, but we can start looking lower and lower packet sizes to see what makes it through. So we started at 9,000. That didn't work. We cut it in half to 4,500, and so on and so forth until we get to a point where packets are actually passing back and forth. So we start sneaking up on the number, and at 1509, we find that trace path once again can't make it through. But if we move it to 1508, all of a sudden I can get all the way through to NRAO. So now we at least understand where in the path we have a problem and what the maximum size we're currently able to push is. So armed with that information, we can now go to UVA campus engineers and say, look, somewhere in the handoff from Maria to you, we've got an MTU issue that's only letting packets this size pass when they're trying to get all the way to NRAO. Can you help us out with that? Turns out they had mismatched interfaces. The Maria router was set for 9192 and the UVA interface was configured for 1518 because again, they wanted to keep their campus at 1500. And that's perfectly fine, but you have to make that change at a routed hop. The routers have to communicate, they have to understand what's happening. And so ideally what happens is your routers facing each other are set to the correct MTUs like Maria and UVA. And then the other side of your router that's going to the campus is then set at the 1500 and change that you want it to be set at. So this broke that path MTU discovery we've been talking about that's crucial for hosts to be able to negotiate an appropriate MTU. This mismatched, these two interfaces that were facing each other and mismatched broke that. So they actually scheduled the maintenance window and they corrected the MTUs. They made it the exact same as Maria. They changed this to 9192. And so now we've got a chance to do some verification on pings between the two hosts. And what we end up with is the syntax here, this -m do says, look, I'm going to send a packet this size, which is 9,000 MTU minus the TCP overhead, but you aren't allowed to fragment it. You have to keep it intact. And when we do that, this is actually what we want to see. Message too long, MTUs 1500. That means the routers are talking to each other. Path MTU discovery is clean the whole way through. And at the point where the MTU changes, the router is responding, look, I can't do that. The other side of the network's too small. You have to let this fragment. And so now if I change this flag, it's kind of reverse logic. If I tell it don't, it's going to allow it to fragment. We change that flag to don't, so saying go ahead and fragment them then, and all of a sudden, we're now getting pings all the way through to the NRAO host, where before we weren't able to do that. So all of that said, what did that look like for performance? So this is the very first test we ran all the way from NRAO to South Africa. We were getting a tidy 380K a second with 58 retransmits, and that's just a short 10-second test, so not good at all. Afterwards, we're getting 2.5, almost 3 gig between these same exact hosts, with the only change we made was correcting that MTU problem that we used perfSONAR and those remote commands we've been talking about, source and destination, to actually run those tests and verify. Now we're getting appreciable bandwidth, and this is without any additional tuning. With some care and feeding, we could probably make this even better, maybe run parallel streams and squeak some more performance out, but just for a quick test, we actually have a clean path now with no retransmits. And at the end of the day, that's what we're looking for, is the ability to transfer science data long distances as cleanly as possible. You want another one? I know you're not responding to me, but I'm going to assume you want another one. This one's a little quicker, but still an interesting use case that we came up. In fact, this one is a little closer to home for most of you. So we got we basically got a request from a researcher that said, hey, I'm running some bandwidth tests. I understand how iPerf works, having some problems getting all the way to this institute over in Japan. Everything looks good if I do TCP testing one direction, but if I go back the other direction, I'm only getting 0.8082% packet loss, but I'm only getting 8 megabit throughput. Over this long path, this is about 250 milliseconds, give or take. This incredibly small amount of packet loss is enough to absolutely crush their bandwidth. The interesting thing, though, is we decided to take a quick look using perfSONAR and say, okay, but what if we do UDP testing? UDP was fine both directions. So what's going on here? So we grab a couple perfSONAR nodes that are along the route, like we've talked about, and we did testing from APAN to Transpac, which is the Seattle node we mentioned earlier, and from APAN to Internet 2 in Chicago, kind of Starlight Exchange over there, and then did the full path. And we're looking at all these individual tests we're running between all these network segments. They all look good. So we're now thinking that the problem has got to be somewhere in CCNY, because it's the only place that we're seeing the poor performance. So we actually put a perfSONAR node in the researcher's lab because we want to get as close to the endpoint that's having performance problems as we absolutely can. So we want to get right there at the end. So we talked to the researcher. He's super helpful, puts a node up. And those tests look exactly like his transfer tests. We're getting one directional loss from his lab out. So now we know we've got a problem somewhere, at least on the campus. So we get NYSERNET involved. They do some testing from the edge of their network into the lab. And through those tests, they actually are seeing that there's some problems even just from NYSERNET into CCNY. So there's a kind of a short path problem there, again, confirming it's on the network there. We also see some packet fragmentation issues like MTU. It looks like an MTU issue, but it's not. It was kind of weird to diagnose it. Just at certain times, packets were being dropped and we couldn't figure out why, but it wasn't really consistent. So with that data, CCNY engineers were actually able to poke around and do some additional local type of troubleshooting. And what they found is they had this old security device that had already been scheduled for replacement, but it just hadn't gotten around to doing it yet. And it was causing packet loss because either a firmware issue or maybe the processor in the security device was just too small and it couldn't handle the data rate. But they ended up expediting that replacement. And as soon as they did that, the packet loss disappeared. And now all of a sudden, we're basically getting our synchronous kind of 80 to 90 megabit, which is what we're expecting across this tunnel. For a variety of reasons, we were never expecting to get 5 gig or 10 gig across here. But now it's synchronous. We get a 10-fold improvement on this bottom end number that before was only 8 megabit, and there's no packet loss. So again, a chance to use perfSONAR to have eyes into the different network segments to isolate the problem to a specific endpoint, and then solve that problem, track down the faulty device, track down the configuration error, whatever it happens to be, and end up with a clean path between two very distant endpoints. So that's the end of my presentation. It looks like I'm pretty close on time anyways. I'm glad you let me get started early, Jason. And that's some of the stuff we're going to be able to play around with in the lab. You actually will have a chance. We've got several different exercises, but as you have some time, you can actually take a look and issue some remote commands and play around with that kind of functionality. So that's what I've got for you.
All right, thank you so much, Doug, for going over that. And we are running a couple minutes ahead, so if people do have questions, they can certainly ask some now. Otherwise, I'll turn it over to Jorge in case he wants to use some of the time to explain the hands-on session. All right, looks like there's a couple questions coming in, Doug, if you want to read them out and answer them.
So I've got one that says, can you describe the community of nodes? So when you stand up a perfSONAR node, there's an option to list it in what we call the directory lookup service. And what that does is your node is now listed in a searchable database that anybody can look up. And if they have a working perfSONAR node, they can now test against you. So you are actually joining kind of a community of perfSONAR nodes across the globe. I think the listing service currently has somewhere in the neighborhood of 3,000 nodes listed in there. So if you're having a network problem, let's say you're doing transfers to this other institution and you want to nail down where that problem is, your first stop can be the lookup service, and we'll make sure to pass around a link for that. And now you can start running some initial testing to this other remote endpoint if they have a node already, and you can start narrowing down what the problem is. Because one of the hardest asks to make of any network engineer is, hey, we're 5,000 miles apart and we're having a network problem. Can you figure that out for me? You're not going to get a lot of traction because that other guy already has a lot of stuff to do, or that other gal already has her plate completely full. So if you can start running some initial testing, you can now go to that other engineer and say, hey, I noticed you had a node in the lookup service. I started running some tests against it. And now I think the problem's here. If you could help me kind of nail this down, maybe we can take a look and work on this together. And so that's really the community aspect of this, is that global infrastructure of perfSONAR nodes that allows you to start your own network diagnostics, start your own troubleshooting without bringing a bunch of different people in up front that may not even need to be involved. You can start narrowing down that problem yourself. So I hope that kind of answers that question. It's common to have a mobile perfSONAR node to move around in different labs. Common, no. It's a possibility. One of the things we didn't touch on a lot here in perfSONAR speak is regular testing. And so typically the nodes are fixed points for a couple of reasons. Number one, if I'm using it as a community service like we just talked about, I want to know where that endpoint is. And if it's constantly moving around, that makes it difficult for me to, as an outsider or even as a network engineer, to use a specific node. The other side of that is perfSONAR needs a real world IP address, an actual routable real world address. It doesn't cope with NAT. So if you're moving it to different network segments, the IP address may have to change, which again kind of limits the usability of it. It interferes with the lookup service and such. And the third part of that is the regular testing. If you're doing regular bandwidth testing, if you're doing regular latency testing, you're going to want that to be at the same point so that you have historical data to go back on. So if 6 months from now you have a problem, you can go back in time and look at those test results and say, okay, well, about 3 months ago, things started to go south. That's where we need to start looking. So I wouldn't say it's common. I could see specific use cases for vetting and testing a network, but I don't know that that's kind of a long-term solution. I probably just have, some more common small nodes. They don't have to be particular high performance, and I would just, if anywhere I thought I needed them, I'd start sprinkling them in. Does perfSONAR troubleshoot bandwidth delay? Can it be used to troubleshoot serialization delay for sub 1 gigs links? It doesn't, it can be used to troubleshoot bandwidth delay, yes. It doesn't have a test that just is going to figure out a bandwidth delay product for you, that sort of thing. But with the information you get from perfSONAR in terms of round trip time, in terms of actual achievable bandwidth, window sizing, et cetera, you can start to figure out if you have a BDP issue where buffer sizes aren't appropriate, that TCP windows aren't scaling to the size necessarily needed for a specific transfer. In terms of serialization delay for sub 1 gig links, no, there's no specific facility built into it for that. Again, there's probably some tricky ways that you could use it to do that, but there's no just kind of out of the box test for that. What kind of performance impacts? That's one we get a lot, actually. So we are cautious about how often we do bandwidth testing. So a lot of people hear bandwidth testing and they freak out because we're doing full speed bandwidth testing, right? If you have a 1 gig link, we're going to test at 1 gig. If you got 10 gigs, we're going to probably try and test at 10 gigs. But we're only doing that 4 times a day, typically, sometimes only 3 times a day, depending on the setup. And it's usually a 10-second test. You can specify longer, but typically it's only a 10-second test. So it's fairly sparse. And granted, if you have 5 or 6 different partners, now you have to multiply it by that. But again, you're talking a 10-second burst and then it's gone again. And then another 10-second burst and then it's gone again, spaced hours and hours apart. The other thing you can do is you can specify test limits. So when you configure your perfSONAR node, you can tell it, look, I don't want you to be able to test 50 times a day to me. You only get 4, or you can even specify bandwidth limits. So you have control over your node. There's a limits file that allows you to specify who can test against you, how often they can test against you, at what speeds you can test. So the performance impact is actually negligible.
All right, Doug, I think we'll stop the questions there, but certainly these are great topics that can be moved over to the breakout rooms when we hit that a little bit later today. So if anybody did have a question that didn't get answered, we'll try to answer it in chat, but otherwise, please come to the breakout session over the lunch break. So Jorge, if you'd like to introduce the next section, I think we're ready.
Yes, thank you, Jason. Very briefly, I saw some comments and Doug was mentioning the limit file, bandwidth delay product. Regarding bandwidth delay product, the next hands-on session, number 2, actually after the one, we will cover that. And all those topics are covered by the perfSONAR lab library, which everyone has access to. For example, the limits file is lab number 10. So these labs will be available for 3 months, but we can always extend if somebody requests. Now, the next item in the agenda is the first hands-on session. We'll be covering the perfSONAR toolkit, the graphical user interface, and how to run this pScheduler. You should have received an email, and if you didn't register yet to the platform, so there is a link here, which is enroll. You click there and just fill the information, and you will have access to the lab library. The presenter will be Jose. Jose is a PhD student here at the University of South Carolina, College of Engineering and Computing. Jose research focused on TCP congestion control, passive measurements using P4 programmable switches, and buffer sizing. Jose is also one of the developer of the lab libraries that we developed here at the University of South Carolina. So prior to joining the PhD program here, he received his bachelor's degree in electrical engineering. Jose, do you want to share your screen?
Sure. Thank you, Dr. Jorge, for the presentation. I will share my screen. So I will introduce briefly the lab library, and then we will jump to the hands-on session. Let me swap this. I hope everyone can see my screen. All right, so the perfSONAR labs consist of 10 labs that cover several topics that Doug already explained. For example, the first steps to configure a perfSONAR node. We talk about the tools, how to configure regular tests using the perfSONAR graphical user interface, which I'm gonna show next. Then we show also pScheduler, how you can use pScheduler. We talk about also buffer sizing in one lab, lab 6. We show how to create a psconfig template. Then we talk about MatDash. We also explain a tool called psconfig web administrator, which facilitates creating pScheduler templates. And finally, we also cover how to configure the pScheduler limits, which was discussed before. Just a brief overview about the lab manuals. Each lab starts with a brief description, objectives, lab topology, lab settings, roadmap, and then in section 1, we provide a brief introduction about the topic that is being covered in the lab. In section 2, we start with the step-by-step direction. You might skip section 1 if you are already familiar with the material. To run this lab, we prepare a pod that consists of 6 virtual machines. You can see on the left-hand side, the perfSONAR pod that consists of 3 perfSONAR nodes and 2 routers and 1 client used to manage the nodes. For example, in perfSONAR 1, we have the pScheduler toolkit and the pScheduler web administrator. pScheduler 2 has toolkit plus the central management that supports MatDash, and pScheduler 3 has only the toolkit. And on the right hand side, you can see that with this pod, we practically cover all the components of pScheduler using the toolkit and the central management. And we also explain in lab 2 how to use these individual tools. So now we are gonna run the lab, which is lab 3. You are welcome to run this lab with me. We will go step by step, and we are gonna configure regular tests using the pScheduler graphical user interface. A brief description about this activity. We have on the left-hand side the lab topology, and on the right-hand side we have the pScheduler layer. We are gonna work on the visualization layer using the Toolkit user interface, and we are gonna, and from here we are gonna configure regular tests. We are gonna access a pScheduler node from the client machine, which is running a Ubuntu Linux, and we are gonna have access to the Toolkit dashboard, which contains all the tools needed to run the regular test. So one more time, we are gonna configure this test, and we are gonna have the results propagated into a dashboard, like we are seeing here on the left-hand side. And also, if you run the test for a long time, you can also have a timing diagram if you click on one of these tests. Just to recap, you are welcome to run this lab with me. If you are not enrolled yet into the platform, I will put the registration link on the chat window, so you can start registering, and you will have access to the lab for 90 days. If you are already enrolled, you just log in into the portal. I will put the link also, and you can run the lab with me. All right, so I think we are ready to do the lab. I will change my screen. I will access the academic cloud. You will see here, I will click on perfSONAR. This is showing me the list of labs that we prepare for this bot, and I will click on lab number 3, so I can schedule a lab for that activity. So the pod is initializing. This pod is hosted in the academic cloud, and you can run labs on your own pace. There's no restriction on this. You can see the pod has been initialized. We have the lab topology here. You can navigate the virtual machines by clicking on them. For example, if I click on perfSONAR 2, I directly jump into the node. And you can also use the tabs to navigate the environment. Yes, sir.
I will just pause you a second because I see some messages. Is anyone stuck on the flashing NDG screen? I noticed that some of you are stuck on there. Yeah, it might take a little bit of time, probably because we're starting so many virtual machines at once. It should be there. The pod should be deployed soon. So I just think it's slow because of the high demand.
Yes.
Suddenly.
That could happen. Everybody is trying to reserve the resources. These are virtual machines, and they have to initialize in order to run the lab. So another thing that I wanna show is that you have in the content tab, you have the lab manual. You can download this manual, and and see the content. So I already downloaded them. So what I will do is divide my screen. On the left-hand side, I will put the lab manual, and on the right-hand side, I will put the lab environment. So go back to the lab environment, click on the topology, and I will run through the lab. So what do we have here? Each lab has the table of contents. As we explained before, we provide a brief overview about the lab activity, objectives, the lab topology. We also show the credentials, which is admin for each persona node. We provide a lab roadmap about the topics that we're going to cover in this lab. In section 1, we have an introduction about a brief introduction about the activity. And right after that, in section 2, we configure the regular test. And here is where we are going to run the lab step by step. In this case, we are going to configure a PerSONAR node from the client machine. So what I'm going to do next is click on the client machine so I can access it. You can see this is a Ubuntu virtual machine. I will open the web browser and type the IP address of a PerSONAR node, which is in this case 192.168.2.10. That corresponds to PerSONAR 2. If you have a warning here, you just click on advance and accept the risk and continue. So the PerSONAR toolkit graphical user interface is loading now. You can see here that we can add information about our organization. And also you can observe the services here. How to add administrative information is covered in lab number 1 of this series. Then we can see the service available in this PerSONAR node, which one of them is pScheduler that we are going to cover in the next activity. I will scroll down and show that we also have a tab for the test results, and that's the thing that we are going to configure now in section 2.2. To do so, on step 1, what we do next is click on configure tests. The credentials, you can see here, if required, the username is admin and the password is admin.
Jose, you may want to pause for a second. It looks
Yes,
like
sir.
there are a number of people getting 503 errors and having trouble connecting to the lab.
That I was able to log in. Let me go back to the lab. I will click on learn. I will select PerSONAR. And I will click on lab number 3.
Yeah, I will answer some question. Is there any VM image available we can run locally? We do have, and we can share. Now this PerSONAR requires for this lab library require 6 or 7 virtual machines, let's say, if I remember well. So
yes,
we can make them available. Absolutely. It's just there is a need to interconnect virtual machines between each other, creating the virtual networks. There are 3 networks. If you show again the topology, Jose.
Yes.
So 6 virtual machines and 3 networks, and there's a need to set up this environment. That's the complex part if you want to do it yourself, but certainly we can make available these virtual machines.
All right. It seems that people are getting into the lab, and
yeah, there are some we will try to figure out what the problem is, and you might want to get out and get in again, so you will take another pod, but we will try to figure out what is happening.
Yes, I can. What I can do is I can just start from the very beginning. I didn't configure anything on this lab again. So what I'm gonna do, I will close this and restart the lab session. Now I will start over this lab activity so you can follow it with me. And I am in section 2 now, and I will start with step 1, where I open the browser. Before that,
and probably just one last thing, Jose. If you are still having issues, you might want to refresh the browser, try it again. It should be loading now. So
yes.
Yeah, it seems that most of the cases are now initializing the pod. Okay, Jose, I will let you continue from here.
All right, so I will start over from section 2. I will click on the client host. I will open the web browser and access a perfSONAR node. You can see here on step number 2, I will type the IP address 192.168.2.10 that corresponds to perfSONAR 2. Again, the perfSONAR Toolkit user interface is loading. And as I explained before, you can see here the basic information about the node. These steps are covered in lab number 1, how to add administrative information. You can add your organization, address, and contact. You can see also the services running here. We can see pScheduler, which is a tool that we're gonna cover in the next activity. And below, there's a tab for the test results that will show the measurement tests that we are gonna run, that we're gonna configure in this lab. So how we proceed? We explain this on section 2.2, and what we have to do is clicking on configure tests. Authentication prompt will pop out, and the credentials are username is admin and the password is admin. After that, we will be able to continue on step number 3, where we configure the regular test. We click on add test. I will just follow the manual here on step 4. We are going to configure a throughput test. We are going to choose that test. We click on throughput. And you can see that we can add some parameters here. Oh, sorry. We will give him a name. I will call it throughput test. And in the next step, I will select the interface. In this case, we have just one interface. Then what I'm gonna do here is setting the time between the tests, which in this case will be 1 minute. I just wanna emphasize here that this is not a realistic scenario. We are doing this in this lab because we wanna have the results propagated into the test result section, and we don't want to wait too much, so we can see some results already there. So that's the reason why we added we asked to set the time between the tests to 1 minute, which is not a realistic scenario because if you have other tests running, they will definitely overlap, or maybe the test will overlap even within this node. So next step, step number 8, we add the participants of this test. We add the IP address. I will add 192.168.1.10, which corresponds to perfSONAR 1. I will give a description. I will call it perfSONAR 1. Then I will add the host. And next step is adding another participant on this test, which is the host 192.168.3.10. And I will give him a description. I will call it perfSONAR 3. I will click on add host, and then I will save this configuration. We'll scroll down and click on OK. After that, you can see that we already added the throughput test here. So to save this and have the test already running, I will click on save. You can see that the interface is very flexible. You can go back and you can delete the test. You can re-edit the test in order to modify. You can see the summary here that we are running a throughput test. We are using TCP. The time between tests is 1 minute, and the test members, we added 2 hosts. So just to recap what we did in this section before seeing the results, I will go back to the topology and explain what we just did. From the client machine, we access the perfSONAR2 node. In this node, we configure a throughput test between perfSONAR2 and perfSONAR1, and another test between perfSONAR2 and perfSONAR3. So that's what we specified in this section, and I will go back to the client machine by clicking on it. And the next step here, step 14, is seeing the public dashboard. By clicking on it, I will click on View Public Dashboard, and the Toolkit graphical user interface will be loaded. Let's wait for it. It takes like 3 minutes to get the result propagated. You can see on the left-hand side that we have to see something like this. We have to see a test where the source is perfSONAR2 and the destination is perfSONAR3. We have to see the throughput in both directions, and similarly for the other throughput test. I will scroll down and you can see that the results are not yet propagated. And what I'm gonna do is refreshing this screen. So we'll see. You can see that the first result, test result, is already present in the dashboard. We are seeing a throughput in one direction, which is around 2.79 gigabits per second. And we still have to wait to see the test results in the other direction and see the other participant. What I will do is refreshing again the windows, and we will be able to see the other test result. So you can see here in the test results section that we have also the throughput between perfSONAR2 and perfSONAR1. All right, with that, I will jump into the other section, and I will configure a latency and packet loss test. How do we do that? Similarly, we click on Configure Tests. We add the test by clicking on this tab. You will see that we will select the type of test that we are going to run here. In this case, we are going to use the one-way latency tool. I will provide a description. Sorry for that. Next, I will select the interface, which in this case is just one. I just want to highlight that this is not a realistic scenario because we are configuring a latency test and a throughput test within the same interface, meaning that the test will interfere. But the aim of this lab is just showing these features, and also you are welcome to use this pod as a testbed in order if you want to explore some features in persona that you want to implement inside your organization, so you can first consider this resource to test that feature. So similarly, after selecting the interface, I will add the test members. I will add perfSONAR 1, 182.168.1.10. I'll give a description again.
Jose, would you, sorry to interrupt you,
Yes, sir.
Hamid is indicating, I don't know how I can open the window the presenter is showing. So could you show again how to, the client machine where you
Yes.
are?
Yes, let me explain that. I'm here in the lab environment. I will click on topology, and to access the client machine, there are two options. First, you can just click on the client machine, or you can also click on the tab here, which is where it says client. I will click on the client machine, and you will see that I am already there. All right, I hope that answers the question. And let's resume here. I will proceed with step number 10 and add the last participant of this test, which is perfSONAR 3, 182.168.3.10. And a description. And after that, I will add the host. I will scroll down and click on OK. And after that, I will save the test. So you can see here that we have some warnings. The first is that the throughput test will be running all the time. That because you can observe here that the interval between the tests is just 1 minute. So that makes sense. And another thing is that the bandwidth test and the latency test might interfere because we are running them on the same interface. I just want to mention that, but I want to also show you something that Doug mentioned in his presentation, which is something that happens when the perfSONAR nodes are close each other. So you will see something after 3 minutes. We are just waiting for the data to get propagated into the dashboard. And what you will see is something very interesting. You will see that some results latency tests might have negative latency, which is because these latency measurements rely on the network timing protocol, which produce an unreliable latency result for nodes in close proximity. And this makes absolutely sense because perfSONAR, these nodes are designed to run measurement tests in a wide area network. And yeah, that's something that I wanted to share with you. I will click on View Public Dashboard.
So there's Ron and Brian have a comment here. They are getting error loading data when trying to view the test details link. I don't know if you had that error before. Yeah, could you comment on that?
I don't know, but we can see that together. Let me just go back to the test results section. And as I understand from the comment, they might wanted to see the details and get that error. This one. Yes, let me explain this error. This is because we just started running this test. For the purpose of this lab, we wanna just guide the user through the experience. So what you might need to do is just adjust the range. You can see here we are displaying results in a 1 week range, and maybe if you select 12 hours, you will be able to see, but not even there because we just started running the tests here. So yeah.
So basically, Jose, if I understand, this is basically you don't have enough test points yet, but this will populate as you keep running the test.
That's correct. That's correct.
Ron, Brian, I hope that answered your comments.
So I'm going back to the public dashboard and I will click on refresh. So let's see if we can see the latency results propagated into the dashboard. Okay, here we can observe the latency results and also the losses. And you can see exactly what I was explaining, that you might see negative latency results due to the proximity of the node. Let me go back to the topology. This pod has 6 virtual machines, meaning that they are running practically in a local network. And yeah, this is not a realistic scenario for running regular tests with perfSONAR node. So to solve this issue, and I am not gonna run through the steps, but I am gonna mention it in the next section. We configure router R1 and router R2 to emulate a wide area network. We use a tool used NETEM, network emulator, and what we do is adding delay to router R1 and router R2, so we can see more realistic results, and also you are introduced to a tool that is very useful to emulate network experiments. So with that, if there's no more question, I will end here and run into the next activity, which consists of running regular tests using the pScheduler CLI.
So you're planning to do with the same pod, is that correct?
No, I will reserve. I have already reserved it.
But can you do it with the same pod? Because I'm just guessing that I know I'm looking at the comments.
Mm-hmm.
Try to save resources, because if you run a new pod, you will need to get new resources.
Understood. So I will try to do that. The only issue is that we have already tests running here and they might interfere each other. So, well, I think there won't be major issues, and it will be very interesting to see that also. So I will just use this pod that is already here, but I will change the lab activity. In this case, I will run lab number 4, which is configuring regular tests using the pScheduler CLI. We deliver this lab in 2 parts, covered in lab 4 and lab 5. And the steps are pretty the same. And you just have to follow the lab. We provide a brief description about this lab activity, objectives. We describe the topology again. We give the credentials, and we provide a brief introduction about pScheduler. So we talk about the tool, and we also talk about the pScheduler command, the basic syntax, how to use these parameters, and also how to get help if you want to know more details or you want to explore another parameter available in the pScheduler command. So with that, what I will do is running a regular test using in this time the pScheduler CLI. To do that, I will go to perfSONAR1, which is this node here. I will click on it, and you will see that I will have access to the CLI. I will log in into the interface by issuing the following credentials. The username is admin, and the password is admin. So after that, in step number 2, I will run a latency test using the default tool. How do we do that? I will type pScheduler. I will specify the task, which is latency. Let's see what happens because there's another test running. The source will be 192.168.1.10, and the destination is 192.168.3.10. Okay, I will submit the task, and
Jose,
we will
I will,
observe. Yeah.
I will just pause for a second. Is there a way to download lab 4 instruction without loading the lab? That way I can reuse lab 3. I
Yes.
already have opened it.
Yes,
So
yes.
I think it's a good comment, and
I'll be happy to answer that question.
Okay.
What you can do is I will put this on the chat window. You can go to our website, click on cyber training, or no need to do these steps. What I will do is I will go down to the perfSONAR library, and
Yeah.
I will share this link here, which contains
it,
all the
it was
links.
already shared by Edley. So,
Oh, thank you, thank you.
so there is a link that was shared perfSONAR lab series. That lab series is a PDF that has all the 10 labs together, and that include all the details.
All right. So let me access that document, the PDF. If you go here, you can see the content and just jump to lab number 3 or lab number 4 in this case. So, all right. So let's proceed and see which results we got. So you can see here, we have still having the problem of negative latency. Let me scroll up by using the following combination, which we specified here, which is shift and page up. If you are using a MacBook, the command is function shift and the upper arrow. So you can see here is where we issue the task, a latency. We are using the default tool, and you can see that the default tool is the one-way ping. And when after the test is submitted, we wait for the results, and we can see the packets statistics here. So yeah, here you can see the results. We also summarize the results here in the lab. You can see you have a full screen of this test, of the results of this test, and also you have the summary with tables and a histogram. So note also that, of course, the results might vary on each run. So in section 2.2, I will show you how to select a tool, a specific tool to run a latency test. Let me clean the screen. And what I will do is use the pScheduler command. I will invoke a task, but in this case, I will use the parameter -- tool, and I will use the tool called twping, the two-way ping tool. This is for latency. And the source is 192.168.1.10, and the destination is 192.168.3.10. So it's .2.10. All right, let's submit this task. You can see that the tool now has changed to the two-way ping tool, and we just wait for the results, and we will have something similar to to the previous test, we will have something like this, and you will have all the packet statistics using a different tool. Here we have the results. Again, you can scroll up or down using Shift, page up or page down if you're using a Windows device. If you are using a MacBook, you use a function Shift and the arrows, up and down arrows. All right, you can see the summary of the results here. And in the next step, we are going to run again we are going to measure the round trip time using the RTT tool, which invokes the ping tool, the ping command that we know. I will just skip this. You can see here on the left hand side that we are using the ping tool, and the results are already displayed here. Okay, so the next activity will be using pScheduler to run throughput tests. As we did with the latency test, let me clean the screen. We are gonna start using the default tool, pScheduler, task, throughput. We specify the source, which is 192. Just a pause here. If you have this issue that you need more time, you can just request it and it will add 30 minutes to your reservation. All right. The source is 192.168.1.10 and the destination is 192.168.2.10. And let's see which tool is using this test. You might guess that the default tool is, see, iPerf3. And as I was anticipating, note that we are already running a throughput test every one minute from perfSONAR 2 that we configure in lab 3, and the tests are overlapping. And the error was that there's no time available for this run. So what I'm gonna do here is just give it a try and try the test against perfSONAR 3. So let's see if this works, if the task finds a time slot to run. And it seems that it got it. Let's see the throughput because we are already running a throughput test here. But I think we had bad news because we have to wait a long time to get this task started. But the result should look like this, where you will observe the report similar to what you have on iPerf3. You will see the report of the interval every second. You will have the throughput, the retransmission, and the congestion window. And at the end, you will have a summary with the average throughput.
So Jose, would you comment why you have to wait 287 seconds, for example?
Yes,
Do you want to comment about that?
Yes. Note that in the previous lab, in lab 3, we are reusing this spot because we don't have, we might not have space. The problem is that there are already regular tests running. Let me go to the topology from perfSONAR 2. And the participants are perfSONAR 2, perfSONAR 1, and perfSONAR 3. So what we did is just manually running a test, a throughput test from perfSONAR 1, where we are here waiting 287 seconds, and it found a time slot. But we have to wait 287 seconds to see that result in displayed here. So yeah, that's the reason why this happens. And you can see before in the previous test when we run the throughput test against perfSONAR 2, you can see that the pScheduler wasn't able to find a time slot available to run this test. Well, what I'm gonna do now is I will just show the tool. I think this is interesting for someone who want to explore the features of perfSONAR, so they can use this spot as a testbed and the lab manuals as a documentation to explore some commands. So what I'm gonna do and finish this lab activity is running a throughput test using another tool as we did with latency. In this case, I will use a tool called NetTCP. I will cancel this. I cancel the task and I will again schedule another task, which in this case, I will select the tool, which is NetTCP. This is a throughput test where the source is 192.168.1.10 and the destination 192.168.2.10. And I will use a parameter here, -I1, so I can show the throughput in a per second basis. So I will submit the task. Hopefully we can find a time slot. So there's no time slot available for this test. Let me do the same as before. I will change the destination node to perfSONAR 3. And let's see if we have a time slot available. And there's no time slot available because the nodes are busy running regular tests. So just to summarize, what you will be seeing is that NetTCP also reports the throughput and other metrics. You can see on the left-hand side here in the manual an example of a test report from using NetTCP. You can see that you can see the command that pScheduler used to run this test, and you can see also the throughput in a per second basis. And yeah, with that, I will finish this presentation. I don't know if you have any question, or if you wanna troubleshoot, or you wanna ask me question, I will be in breakout room number 1.
Well, thank you, Jose. And we apologize for the technical problems we're trying to fix, and hopefully I expect that the next hands-on sessions will go smoother. So we are adding capacity right now. That means more pods. Yeah, hopefully it's gonna be smoother. So Jose, I think there is a comment. I don't know if you want to address the comment or a question.
Sure, let's see. Bill says that does this argue for having less regular testing on production pScheduler servers, so there's more opportunities for ad hoc? So yeah, usually as I understand from my experience on perfSONAR, and also Doug mentioned that you don't run these regular tests every minute. You run them like 4 times during the day. And yeah, and we are doing something a bit different here, which is overlapping the test by spacing them out every 1 minute, which is not realistic. That means that you are using your network just for measurements, and that's not how perfSONAR works. But the aim of this lab is showing how this tool works, and that's the reason why we are specifying such a short interval.
Yeah, and there is also a comment from Brian. That's what I did with the perfSONAR servers. It took a while to get it set up just right. but I have got bandwidth tests set up to where it only happens from midnight to 6 a.m. That's a good observation. Less busy hours. Okay. So, Doug, I don't know if you want to, I see your comment. Do you want to read, or you want me to read this? Or do you want to comment on that?
Yeah, it was a great comment about establishing test limits and how much testing you want to do. So your node can be involved in multiple different testing meshes for regular testing. And honestly, there's actually provisions in the configuration for bringing a node that isn't actually a part of your mesh, but you want to include it in your mesh, and doing that without the node owner's express knowledge, basically. You really want to be careful with how much testing you're doing, and that you're doing it to valuable endpoints, ones that have a direct impact on the research that you're doing, network paths that you need eyes on to know the regular performance. But it doesn't take a whole lot of testing to do that. 3 to 4 times a day is more than enough. And depending on the limits that you set, maybe, again, specifically doing testing at specific times of day is even more valuable to you. Using that pScheduler plot command is really, really handy, because it's actually easier to oversubscribe a node if you've never managed one than you might think. Because all of these bandwidth tests are exclusive, they have to be time slotted. So you can use that pScheduler plot utility to take a look at just how busy your box actually is, and maybe then based on that, make some decisions about, we're doing this regular testing that we don't really need to do, so maybe we could back off of that, or maybe we don't actually need to participate in this specific mesh. So there's a variety of different tools you can use to understand just how busy your box is, but definitely try and leave some room for that ad hoc testing, because that is really valuable for network researchers and for people like myself that do a lot of performance analysis, where I need to have at least a time slot where I can get in there and do some testing off the cuff just to understand what's going on. So what I encourage people to do is be very intentional with what data is actually going to be valuable to you 6 months from now or a year from now, versus, hey, I've got a new node, I want to just see it out there testing and doing stuff, and just, think critically about what's of real value to you in a historical context when you're choosing what scheduled testing you want to do.
There are a few other.
I was going to say that, yeah, there's one more question. Is it better to do testing at the same time or vary? Interestingly enough, there's a slip rand command in your test definition. So let's say you're bandwidth testing every 6 hours. Now you're doing it 4 times a day. There's going to be a slip rand feature in there of plus and minus whatever time period you set. So if you set it for 1 hour, that means I'm going to try and schedule this at, say, 10 in the morning, but I can push that test 1 hour either way from that 10 a.m. time slot, depending on how busy the server on the other end is, or if my node happens to be busy right at that moment. And if you increase that slip rand amount to, say, 2 or 3 hours, it can push out even further if you want that to happen. So there's no real facility for saying, I'm going to test at this time on this day and this time on the next day. I mean, if you had some really complicated configurations, you could probably get away with that. But usually that randomness factor that is built into perfSONAR is enough to give you kind of a different look where it's not exactly the same time. One thing I would encourage you to do is, again, if you can look at your local data in terms of bandwidth, maybe try and schedule tests at times where you want to know what it behaves like, say, before everybody's on campus. And then what does it look like around this time in the morning when it's typically very busy? And what does performance look like maybe at this time in the afternoon when it's not quite as busy, but there's still a lot going on? What you're trying to do is generate a picture of what your network is doing at various points in the day. And so what we're testing isn't actually your maximum bandwidth. What we're testing is what you have left over. If you have a 10 gig pipe and there's 3 gigs of background traffic, you're only going to see 7 gigs. And so at different times of the day, if you have some kind of intentional tests set up to understand what your network looks like as your network is more or less busy, that can be kind of valuable in terms of, we're having problems every day at 11. And we look back historically over the last month, and we've been bandwidth testing around that time. And it looks like our 10 gig pipe is full at 11 a.m. every day because there's so much going on. It can help you start to pinpoint how much bandwidth and where that is. Any recommendations for cheap hardware for perfSONAR nodes? Yes, Raspberry Pis, the new version 4s actually have a real NIC on them. So the version 3 and lower is a USB 2.0 connected NIC, even though it looks like it's a physical NIC, it is not. So they can cope with local testing at 1 gig, but that is it. Other than that, you start adding some latency in, you get 20, 30 milliseconds away, they really start to struggle. There's just not enough there. Plus, perfSONAR node's designed to be an always on, always accessible resource, and the Raspberry Pi hardware typically struggles a little bit in what we'll call a production environment. Actually, what I really recommend if you're looking for a low-cost node is something like this guy right here, which let me turn my background filter off for a second. So this is a Intel NUC. I recommend getting the Core i3 version. There's a Celeron version of this, but the Celeron seems to have a little bit of trouble keeping up with 1 gig testing. The i3 variant, which is what I've got in my hand, this is a 8th gen one. They probably have a 10th gen out by now. It's going to cost you a little bit more to provision one of these. You're probably talking with RAM and a small SSD, maybe in the $350 range. But we've had really good luck with these holding up years and years and years of production. They're a really solid little unit. They don't have a big footprint, and at idle, they consume less power than a nightlight. So that's probably my go-to recommendation if you're looking for a low-cost node. You can put up a 10 gig capable node, though, just a very basic, say, super micro style pizza box server. You can get one of those up and going in the $1,500–$1,600 range. And now you actually have a server level motherboard, you have 10 gig capable hardware, and it's really not a bank breaker for most people. So there are some different options out there, but those are kind of my 2 go-to recommendations for relatively low cost stuff. Network testing performance throughout various campus buildings. Do PS nodes need to be installed and PCs in each location? Is there another option besides using PCs? Yeah, the NUC's probably your answer. For doing initial on-campus testing that you actually have more control over, you could probably get away with Raspberry Pis if you're fine with the 1 gig limit. If you want, if you're trying to get data from 20 different locations and don't want to spend a fortune doing it, that might be a good way to get your foot in the door. Again, I wouldn't leave a Raspberry Pi out there as a long-term production device. It's really not suited for that. But if you just want to get some kind of quick, interesting type of information, that might be a good way to do a 1 gig test in a pinch.
So Doug, I think we're going to need to pivot to doing the breakout rooms here at this point, but these are all really great questions.
Yes.
So Christy, if you're ready to open them up, I say we get them ready and then we give people instructions on how to get. All right, looks good, Ken.
All right, thanks. All right, hello everyone. This talk's going to be kind of overviewing of the Science DMZ, looking at different various design patterns of the Science DMZ, different data architectures, and where also to locate your DTNs depending on the science and some of the engagement you may have with your users. So as we step into this, a lot of times campus utilization is broken down by, how can the infrastructure handle the users that are out there based on the number of users or the amount of demand that's out there based on capacity and, utilization in general. But, when you start adding, large research compute jobs and transfers and things like that, and how well can the campus infrastructure typically handle this? A lot of times one researcher's job can actually dominate, and take actually more cores than a VM infrastructure on a campus. In addition, there's also, more storage than an entire department. There's also more network capacity, the entire campus Wi-Fi, and that's just one researcher. Just depending on where, where these, folks are working and things like that, those kind of things come into play. Many times campus infrastructures are typically designed around what's called speeds and feeds of network access, number of services and VMs and to run servers, and also storage to facilitate those existing services. But a lot of times data is not really typically generated, from a campus, just from an enterprise perspective, unless it's more like database type functions and things like that. So, but a researcher might be able to generate multiple parallel data sets related to different types of analysis or different types of jobs that they're running to do their analysis on any sort of the work they're doing. And so a lot of times campus infrastructure is measured via uptime, availability, SLAs, and pieces like that. But when's performance actually measured? Most of the time it's really measured after trouble tickets. And that's what we're kind of focusing on here. So if we, kind of change the paradigm a little bit to more of a performance first focused, the utilization will just come naturally. So some of these use cases, as you engage your researchers or you look at your flow data, those kind of pieces come up that who are your heavy users, and you can kind of address this accordingly. So many times data transfers look at something like this, where you have, a server somewhere buried in the network behind a access layer switch in a campus closet, connected out to the core, out to the perimeter firewall through the border, and then it goes out to the world. And, this works, it works for what it's intended to do, but many times the size of the data sets, the researchers really have a long time to wait for transfers to happen, or they have limited access to where the transfers can go to and from. There might be other bottlenecks, like, some of the comments, from the previous talk with Doug, some of the network troubleshooting, and some of these systems are like this, where a server is buried somewhere in the network, and you have to break down all the different components to get to and from the end-to-end solution to make sure that it's performant. And so a lot of times also researchers don't understand where they should be on this performance chart. What expectations should they have for data transfer performance and accessing certain resources and different data sets around the world, and even across campus, for example. So this is a chart that we have. We'll kind of review this a little bit later, but when you have a chart like this and researchers can see and understand, as well as IT services know where they should be performing at, that paradigm shift is something that can happen on both ends, so that really researchers and IT kind of understand the requirements, but also understand what the resources can do. So there's kind of a a happy point in the middle where you can meet and understand what each other's is offering and what each other should be expecting. So this kind of chart will help you get through that as you look through different resources. So going off the same type of thing, but why not both? So if you look at this, if performance is included in campus design, so that there were areas of the network, areas of the campus where where there are large instruments or large microscopes, sequencers, cryo-EM machines, or there was a new one I just heard about yesterday that's even bigger than cryo-EM. So that is doing something with 4D images and something else. But anyway, these producing, terabytes an hour of data. So be able to move that around a campus that's not prepared properly is really going to saturate functions or just take a long time. Or unfortunately, the researchers will dump everything onto a jump drive or a remote hard drive and carry it across campus. And, that's the last thing we want really, is going back to SneakerNet for these type of situations. So as you get into this, think of this, this is a slide actually, some comments in here I actually took from Jason. Think of this as a content as a reset. We don't want to build the IT for the sake of building IT. We want to tie the infrastructure back to the user and use cases and be sensible about design, installation, security, performance, and the operation. And one reference to this is going to a Science DMZ design and with the engagement of researchers. So the science DMZ design, if you haven't seen this before, otherwise many people have seen this probably too much, but the design pattern is out there where for a large transfer to and from campus, you can put a high performance data transfer node either with local storage or connecting back to additional storage on campus that is really isolated down to only do the transfers to and from via security controls to and from the endpoints necessary or to and from the applications. Otherwise, the server is completely locked down from any sort of a random access. And by doing this, you take the heavy load off the firewall for these large data transfers, and you provide the data transfers to go to and from the remote site as it needs to and as performant as possible. So as we get into this, different campuses have brought up needs because not all campuses are the same. Not all border perimeters and border firewalls are laid out the same way. So we've kind of come up with a few different science DMZ architectures to take a look at. And so we're going to go through this a little bit. And as we do this, we talked about the different components that go into a performance network or performance-based network, where you have a friction-free network path so that the high capable data transfer nodes can do the transfers at the speed they can transfer at and as they're tuned to do. These highly tuned machines can really send data out at a very rapid rate or receive data quite efficiently, more so than just dropping a server anywhere on your network. So paying attention to performance in this setup can really help out and really save time for the researchers, as well as create a nice security paradigm to know what's going on with this individual device and also with the data sets that are going to and from that server. In addition to that, the perfSONAR tools that Doug was going over earlier, having one of these at your perimeter will really help out to find, whether it, is frankly your problem or our problem. So that's where, if you say, having it at your border, you can test to the outside world, and if you're getting more, traction or more bandwidth out the other side, then it's not your problem. But if it is happening on your campus, then it is your problem. So just having a single perfSONAR server at your border will really help you troubleshoot a lot of these problems. And then from there, there's multiple ways to put perfSONAR around your campus, depending on where you have large data transfers or you have performance criteria you want to be able to meet. It's really just a kind of a Lego block you can kind of plop down anywhere you want to. Then the other piece about a science DMZ architecture is the engagement of the users. So understanding, where these researchers are and what kind of equipment they have, what kind of transfers they have, how large they are, how often they happen. All these things can come into a planning exercise and understanding, where you can, build out your infrastructure to be able to support this type of work. So those are the 4 pieces of the science DMZ. And one of the previous directors at ESNet was looking at this, say, as researchers have their compute and they have their storage and they have their applications, a lot of times what really is missing is the network is a major component of that. And it's kind of like the vascular system of the research workflow. So things cannot get from, one side to the other or from one collaborator to another without a network in the middle. So if the network is able to be created as an instrument as well and tuned properly, the same way you would adjust your compute and then adjust your code to compute more efficiently, or the same way you would set up your data storage to be able to be more efficient and be able to handle large files, small files, and the way you would tune an application, these all come into there. But a lot of times the network is often missed, and this, treating the network like an instrument as well, the way you calibrate it, could really go a long way to ensuring both data transfer times are reduced as well as collaboration between researchers. Another component of this breaks this down a little bit differently. The 4 components we talked about earlier, this is just a similar diagram to that. You can kind of see how they all mesh together. It's not just one piece that comes into this, but it's really a combination of various efforts to try to make this the scientific workflow more efficient, and then also help with the data transfers on a campus network to be able to be more efficient as well. So stepping into some of the designs, I have a few designs out through here for different data architectures we can take a look at. So we talked about this diagram a little bit earlier, just a basic simple science DMZ for large wide area network flows. And we talked about a few of the, I guess, benefits for having this. You know, it's a very simple piece. There's very tight security controls you can put on each component. There's not a lot of hardware to deal with, just kind of is set up, it's tuned properly, it's locked down, and it performs very well. So going into this is where it gets a little interesting, is where every campus is different, every scientific workflow. I mean, there can be similar patterns, but until you have a researcher coming to you saying they have a problem, or they're getting this new piece of equipment, or they just want another grant or want a new grant, and it's going to be happening. So we need to figure this out, but you don't have all the requirements yet. There are various ways to kind of set up these, and these different data architectures are going to kind of go through that. So with this one, the way that an individual data transfer node can be set up by project. And so this doesn't have to be right next to your border router. You can actually, if you have fiber across your campus, you can actually home run the DTN at the local site back to your Science DMZ switch or router. And this will benefit in a number of ways, because you have a large enough switch and router to be able to handle the wide area transfers. In addition, you can actually try to get the data off the remote project and the remote location where the instrument may be set up. So this allows you to take the Science DMZ and extend it into a campus perimeter without really running across any other part of the campus network, and to be able to get data to and from the instrument. The downfall to this is you only have a single piece of equipment back at the edge. So there's just a single DTN can be connected there. Each DTN can have its own security policies and setup on there, but from there, this is just one example on how to do that. And I've kind of gone through some pros and cons here. Take a look at those. From stepping a little further is you have dedicated switches on each project. So you have the border router really building multiple Science DMZs out to these individual locations. And this could be based on data compliance, data policy, really a number of ways to do this. A dedicated instruments, it could be something like an open science grid cluster in one area of campus, and it could be a cryo-EM on another area of campus where you kind of have this distributed. One of the cons to this is you have to have multiple sets of equipment. So you need to have the Science DMZ switches and routers need to be able to have deep enough buffers to be able to handle these larger transfers coming there. So it's multiple large sets of equipment that you would have to support, but at the same time, these are developed around different security profiles and different data transfer sets that can get into it. Here for anything else. Again, this keeps the large science flows off your campus network. The DTNs can be custom tailored for the actual workflow on the job. Another design that some folks have looked at is how do they connect their HPC so that they can integrate perfSONAR and data transfer nodes, a parallel file system to some of these locations. And this was a slide that was set up to kind of address all those individual pieces like that, related to this, using the Science DMZ design pattern and including all the 4 elements related to the Science DMZ architecture. And getting into this, you can see how there's multiple switches there, the multiple data transfer nodes connected to the parallel file system, and you see the supercomputer and the way that it's set up there. Another approach that's similar to this is if you break that down a little bit further, and then you keep your campus compute nodes and your file system back on the enterprise network or back in your data center network, having individual file and security controls based on this data, you can actually engage the Science DMZ pattern so that you create a cluster of DTNs on the outside, so that these cluster of DTNs will provide you resiliency, provide you scalable bandwidth related across the data transfers, as well as if you need to take one down for maintenance or patching, you still have the other ones there available to do this. So this was a way to set up cluster DTNs connected to the parallel file system or remote storage that allows you to kind of address all the needs, maintaining the Science DMZ design pattern, but in addition, creating some isolation between your cluster and head nodes, so they're not really on the outside world, having people log into them from the outside. Those would still go through your campus and your perimeter firewall. One thing about this too is on the pros on this one, you don't need to do the double copy. So when you're first starting out and you put a DTN on the outside with local storage in it, you might need to copy there the first time, and then you might need to copy onto your local campus storage a second time once you get the data to your DTN, then pull it back into where your compute and storage might be located, or towards some analysis machine locally on campus. So that kind of piece, that preventing the double copy transfer with this cluster DTNs really can go a long way to, increasing performance and cutting down speed. And frankly, a double copy workflow is sometimes still needed, but this is the way you can kind of get around that. So the other piece around this too is you kind of separate out your data transfer node and you create the data transfer portal and put that inside the campus. And then you only have access to the data transfer nodes via the API to the application. So we're going to go over that in a little bit, but this model here with the cluster DTNs allows you to separate out the data portal on the website from the actual data transfer process and the data transfer application. So as we get into this is a similar diagram I had from the beginning, where you have your portal server based somewhere within your network, going through the enterprise network, through the perimeter firewall, and stepping out through there. So as you get into this next generation portal leverages the ScienceDMZ data transfer pool as well as a central data store. So how this comes into play is the DTNs themselves only have API access to the outside world. There's no other way to get into them unless an out of band management or something, but the actual outside world, only the API can access those. So you initiate a transfer by going through the wide area network, down through the perimeter, down to the portal server down here. And this can even be a container based solution at this point. And as you're doing that, you request your transfer, it kicks off an authentication and a transfer job process. And then that comes down to the DTNs, that gets coordinated, and then you can do your data transfer back and to and from your file system through the ScienceDMZ. So this is your request and your authentication path and authorization path when the actual data transfer kicks off this way. And there are a number of public examples of this working, and it works very well and it works very efficiently by separating out the two components of your data transfer nodes and going through those pieces. So just again, more some pros and cons here if you want to look over those later. Another data archive to take a look at is if you have a large instrument on campus and you need to be able to set up and understand how to get data to and from that instrument. Sometimes the least equipment that comes from a large instrument is pretty locked down, and you need to keep it on a private network because the patching for it is sometimes not as efficient as you want it to be on these control PCs. So what you can do sometimes is create a pass-through directly to that, where you have the storage actually land on the data transfer node or the actual shared storage itself. And you can kind of use the ScienceDMZ design pattern inside of a campus right next to an instrument so that you can make the transfer more efficient versus just using, a lightweight, say Windows machine here that will run, will control the instrument, but is really not able to handle the transfers very well. So if you mount the drive back to one of these other locations, the data transfer node can be the efficient way to move the data around campus, whether it's out to the outside world or whether it's back across campus network towards your HPC and your centralized compute versus your local compute here. So again, these are like Lego blocks that you can keep working with depending on where your bottlenecks are, where your transfers are, and then being able to understand to and from, where the transfer is going and what the researchers need. So two other pieces that have come up through EPOC that are pretty interesting is sometimes people believe that the ScienceDMZ needs to be a separate, research network that's parallel to the enterprise, that is completely air gapped, or they only connect up with the border router. And then, but desktops and NAS systems and compute nodes and GPU machines are all sitting on this this public research network that's out there. And a lot of times this is really limited to only research and education networks. So it limits access to cloud and other services like GitHub. and this is typically it's unusable. Some people have complained that, you know, while they can do certain things very well, other basic functions they can't get done. So one of the recommendations was just to try to integrate this existing research network with your enterprise network to make it more usable, and then re-engage and refactor your science DMZ for the transfers. So it's not really taking anything away. It's just, you know, looking at what you've deployed and then, you know, refactor this to make it more usable as well as secure, but also make it more performant at the same time. Another use case and example is some large campuses operate more like an ISP, where they have central IT and they have distributed IT and the local areas, the research areas, as well as, you know, administrative functions. So the IT support is very disseminated across campus. And looking at this, you also have border firewalls, you have separate data center firewalls, you have firewalls in front of wireless, you have firewalls in front of campuses and different departments. So even to try to get data off an instrument like a cryo-EM across campus can be somewhat difficult at times. And one researcher actually was stating that the transfers off campus to another collaborating university were faster than transfers across campus within the same segment of the campus, you know, a few buildings away. The transfers are different. So numerous MTU mismatches were found on the networks. So the recommendation was, you know, to tune for the jumbo frames and you try to build a science DMZ pattern that works to bypass the data center firewall and allowing only the traffic from the DTN for the cryo-EM to be set up. So these are again different use cases that are out there to take a look at. As we step into this with the different data transfer nodes, the original design was back in 2012. I think the concept had been, you know, 2010 to 2012, there were different presentations and different setups as we started discussing these type of design patterns. The idea is really around the server is really designed and built to do data transfers directly, nothing else to do, and that's it. So as you get into this, the different components around there, you limit the application, you limit the security profile on the outside. Then as you get into this, the other piece is typically you can have local storage on there, but you can also connect remotely to remote storage. So as you get into this, the other pieces come into play where the DTN and the perfSONAR node, you can set these up directly right on the security or the router at the border, and, you know, make sure you have all the components within the science DMZ for this. One thing about this, a 210 gig server, as we're finding, is actually much more efficient than just 25, 40, and 100 gig servers that really are just plugged in. There's a lot of tuning that can go into a server that can make it much more efficient. So you can save quite a bit of money by going with a 10 gig server and have it tuned efficiently back to a central storage, and then going from there. Multiple DTNs, like we talked about earlier, cluster DTNs together can perform quite well, but also provide you some resiliency. So instead of spending a lot of money on a single 100 gig server, you know, 2 or 3 smaller 10 gig servers can perform, you know, much more efficiently, as well as provide you some downtime. But the key takeaway here is to make sure you match the DTN capabilities of the site and the wide area infrastructure, as well as what the researcher may need. Some of the other pieces around DTN considerations to look at, you want a single resource for moving the data to start with, and then working with individual researcher or an individual project. So from there, you can step this up, and then you look at try to get a NIC that you can find that works for your campus. Typically a 10 gig, like we mentioned earlier. Some sites are starting to go from 40 down to 25. That's more common on newer switches and within data centers. In addition, you want to try to have direct connectivity to the outside, as well as a faster clock speed for your DTNs. Multiple cores, usually 8 and up, allow you to run parallel transfers at the same time to be more efficient as well on the data transfer node. And then again, make sure your storage is allocated appropriately, whether it's local or with something tied to something on the back end. Here's an example of a DTN we just actually put online in the last 2 weeks. So some of the numbers there you can kind of look at and, you know, look there. And then I included a URL at the bottom if you actually want to test transfers to and from this DTN. we talk about data mobility benchmarks. So this is something that on the data mobility breakout room, we can kind of go over, and I have a separate slide deck for that. But what this allows you to do is really test and tune your data transfer node in your Science DMZ, including your perimeter, to make sure you're running the appropriate BGP path, and also testing your storage read and writes. So these are a series of links you can go out and to click on and try to run these, or you can see me in the data mobility breakout room, and we kind of step through a few of these and try them out. One of the final things here is we have a data transfer scorecard that we're trying to work through and try to get people to understand this. So with EPOC, we're trying to make sure that researchers can transfer at least 1 terabyte per hour. And that turns into roughly 2.2 gigabits a second, or from a sysadmin or storage perspective, 277 megabytes per second. So having those numbers, depending on the audience, will really help us understand kind of what each other's language we're speaking. But really the baseline is we're trying to focus on, to the researcher, 1 terabyte per hour as a baseline to start. And then from there, you can kind of do some tuning and try to increase from there. But if you're not getting these numbers, please, give us an email, give us a call, so we can help you with these transfers. But this is kind of the baseline we're trying to work from to kind of raise all boats, if you will, so that everyone can be more performant when it comes to these cyber infrastructure grants and the implementations we're doing to support our researchers. Some of the other pieces around Science DMZ and DTN tuning you can take a look at. The MTU is the biggest problem we run into. Mismatched MTUs, like Doug alluded to that earlier in the perfSONAR talk. And there's a link here to an EPOC paper on the MTUs. Adjusting your BGP to prefer research and education networks. This is a big one, so that your traffic doesn't go out and go over commodity networks. Running traffic through, like, for example, NYSERNet is typically more efficient than your commodity network, depending who your provider is. Setting up perfSONAR on your border router, we mentioned earlier. Research the modern research data portal, which I covered a little bit ago, about separating out the authentication authorization in the portal website from the actual data transfer services. Something else you can also do is set up top 10 source and destination reports to keep your eye on large transfers, who your large transfers are happening to and from. If you don't actually have tools to do this, you can probably look at your NetSage instance, either from your regional network. They may have access to this data and be able to help you troubleshoot who your large users are with the transfers. Again, well-tuned 10 gig servers go a long way versus a single 100. And one other piece around restricted and controlled data, if you must have something behind an enterprise firewall, to make that more efficient, a lot of firewalls have what's called an ASIC-based transfer path. So sometimes they brand that as fast path or express path, depending on your firewall vendor. So this is a way you can still make certain conditions go through the firewall, even if they need to be able to go in a more efficient path. And then I also included a link here for DTN tuning. So. Yeah, so any questions?
So thank you, Ken. We did have some questions that came in during, but we hammered down most of them now.
Okay.
There's one that's coming in right now. I'll just read them and you can answer them.
Okay.
Is fast path similar to cut-through switching?
No. Cut-through switching is really on the data center side. It's really we've run into a few issues with people buying data center switches and plugging them into their Science DMZs because they don't handle large transfers very well, and they usually have dynamic buffering within the switches. So the transfers can really be affected by cut-through switches. The ASIC-based pass is a firewall process. Once it checks the data transfer, that will run it directly to there and not process the rest of that flow. So that's just a few things we've run into in the past, and just a recommendation for looking at those type of things. So.
Okay, and we'll get one more, and then we'll need to transition to the next one. Any new alternatives for BBCP?
I mean,
BBCP is the I want to say it was developed by Slack, but it's sort of similar to Grid in nature.
yeah, typically a lot of for the data portals and things like that, typically we use the Globus next generation portal with the Globus system on the back end for distribution of data. For bulk transfers, there are a number of tools out there that can be used, but typically there's a number of ways to use the Globus API to automate workflows related to things like this. So if you're trying to make something more programmable, and I think Globus has a new system called Flows, you can plug that in there and actually make things like that work much, quite a bit more efficient. For the actual transfers themselves, I mean, there's a number of tools out there. It just depends on the frequency of the transfers, the authentication, who's going to get them. There's a number of, there's a lot of variables in there. So there's also a lot of tools. It's just, like I said, say pick what works. But typically, if you're trying to set something up for, data coming off of cryo-EM, set up the modern research data portal with the Globus API, and you're kind of done. So.
Okay. And just a comment, send your slides off to Jorge and his team so that they can get them posted, because several people have asked.
Yep.
And with that, I will hand it over to Jorge to transition to the second hands-on session.
All right, thanks.
Thank you, Ken. Thank you, Jason. Yeah, we have a second hands-on session. I will share my screen, and then I will let Eli lead this session. Hopefully this will go smoother than this morning. We'll have a hands-on session on TCP bandwidth delay product. We talk about BDP, the bandwidth multiplied by the delay, and that's a number that is quite relevant because the TCP buffer and the router's buffer size use this number. So Eli will go through these labs. The PowerPoint slides are already online, and we will be uploading the rest of the PowerPoints later during today. Now, if you didn't enroll yet for this hands-on session, this is a different library than perfSONAR. So please feel free to do it. Here we have the URL. Now, this library, we will not cover all, but there are many other topics that might be of your interest. For example, what type of congestion control, what is the performance of different congestion control algorithms? There are several labs that might be of your interest. And this will be available after the workshop as well. So I would let Eli to share. Eli, could you please share your screen, and I will briefly introduce you.
Sure.
So Eli is a PhD student here in the College of Engineering and Computing at the University of South Carolina. He's doing research on P4 programmable switches, buffer sizing, dynamic buffer sizing. He's working in several projects. Before coming to UofSC, he received his master's degree in computer science from the American University of Science and Technology. Eli, please feel free to proceed from here.
Thank you, Dr. for the introduction. So hello, everyone. On this hands-on session, we will be going over some tools that are very relevant whenever we want to emulate wide area networks, and we will see some recommendations whenever we want to tune our end devices to get better throughput. So we will be briefly describing the platform we're using. Specifically, it's called MiniNet, iPerf3, why TCP buffers are important, what is a BDP and the TCP window. And then we will later on during the hands-on session, we will see what happens if we don't tune those send and receive windows. And then after we tune them, what is the throughput gain that we have? So I will skip over this. Dr. Jorge mentioned it. This is the list of labs that are available in this lab series. So in this lab series, we decided to use Mininet. Mininet is a software that allows us to perform network emulation. And basically, we will be using real Linux network stack for the end hosts. So sometimes we call these containers, but more accurately, it's called network namespaces. So the devices like the hosts here in this topology will be inside network namespaces. And the containers consume sufficiently few resources that networks over 1,000 of nodes have been created running on a single laptop and also achieving very high rates. To be able to create the topology, we will be using a graphical user interface editor called MiniEdit. And in this editor, basically, you can drag and drop these different devices and make the connections as you wish. Some of the devices that are available there are hosts. So these are regular Linux-based hosts where you can issue any Linux command. You have also switches. You have software. Both of these are software, actually. So software switches, software routers, and basically, you need to connect them through links. Once you have that topology there, you can click on run, and this is going to be deployed on your machine for emulation. Now, in our labs, we already created the topologies, and they are saved in files, so we will just load them. We don't have to recreate the topology for each lab. This is an example here with the minimal topology in Mininet. So we have one switch and two end hosts. And if you want to emulate something like this, all we have to do is just insert two end hosts here, H1, H2, have a switch, and then basically connect them. And once we have it, we click on run, and the devices are ready to start communicating. So if you try a ping test or an iPerf, it will work immediately. Now, the default IP addresses that are used are in the network 10.0.0.0/8. And the convention here in Mininet is to use the host IP here .1 based on the host name. For example, H1 will have 10.0.0.1, H2 will have 10.0.0.2. If you have H3, it's going to be .3, and so on. So a brief introduction on iPerf3. Where is iPerf3? iPerf3 is a real-time network throughput measurement tool. It is open source and is client server based. So we have to launch a server for listening to incoming connections, and the incoming connections will be basically iPerf3 clients. So we can basically say that I want to start a server on this host here and a client to connect to that server, and we'll start pumping data. And based on the throughput, we will get a report at the end of the test telling us the amount of throughput that we got during that test. And iPerf is interesting because of, we can measure the throughput, and it will allow you to troubleshoot a lot of problems as we've seen in the previous slides. It can operate on TCP, UDP, SCTCP. It can work in both directions. It can be unidirectional or bidirectional. And this is an example here of a report produced by iPerf3. So you have the intervals, and then you have the bit rates achieved per interval. And also you can see the total amount of bytes transferred for that test. So we will be doing lab number 8 in the series, which talks about bandwidth delay product and TCP buffer size. Just to give a brief overview on TCP buffers. So TCP has the send and receive buffers, and they can greatly impact the performance of data transfers in a wide area network. So on the sender side, so we have a TCP send buffer. TCP will accept the data from the application, and the data is placed in the send buffer. Typically, it's based on the maximum segment size. In this example, it's 100 bytes. And then these segments will be transported over the network and sent to the receiver. Now, once it reaches the receiver, they're going to be received at the TCP receive buffer. And then this data is delivered to the application in order. Okay. And basically the receiver will be sending back the acknowledgement for the segments that are being sent from the sender. And the idea is these buffers here, there's their space, or how much available space you have, will basically give us an idea on the throughput. So the receiver will be basically indicating the sender how many bytes they can send based on how much free space you have in the receiver. So this is why the buffer size here in the TCP send and receive can impact the performance of the network and the throughput that you can achieve. Just to give some few numbers, if you are assuming that we have a TCP buffer size of 1 megabyte and a round trip time of 50 milliseconds, and also if you assume that we have a 10 gigabits per second link, then the value of bytes inside this buffer, which is around 8 megabits, will be transferred in 0.84 milliseconds. And this means that after 0.84 milliseconds, so this data was transferred, the TCP send buffer will be empty, and it must wait for the acknowledgement from the receiver. And because we have a 50 millisecond round trip time, so we have to wait for 50 milliseconds to receive those acknowledgement. And this means that the sender will only be using a very small percentage of the available bandwidth. In this specific example, around 1.6%. So tuning these buffers is very important to get the throughput that you are aiming for. So how can we fix that? What value should we set this TCP send and receive buffers to? So we have the quantity, the bandwidth delay product, which is basically multiplying the bandwidth by the delay or the round trip time. And basically this number of bits is the value that can be transmitted in a round trip time period. So here an example for the same setup that we've been using in the previous slide. We have 10 gig, we multiply it by 50 milliseconds, and we get around 62 megabytes. So this is basically the bandwidth delay product. And we want to make sure to set the TCP buffer size to at least 1 BDP. Now, in Linux, there are some observations that you have to keep in mind whenever you send and receive buffers. Linux by default assume half of the value that you set for internal structures. So if you are planning to set it to 1 BDP, you have to set it to 2 BDP so that you are really using 1 BDP for the TCP buffer size. So in our case here, for 60 megabytes, we will be setting 120 megabytes. This is the topology that we'll be using in the lab. So we have 2 switches, we have 2 end hosts, and there's a bottleneck link of 10 gigabits per second. So we will also see how we can configure this bandwidth here to be 10 gigabits per second. And also we have 20 milliseconds of round trip time. So also we will show how we can configure this round trip time, how we can emulate it. And then if we just run a iPerf test at this point, we will see that the throughput that we will get is around 3 gigabits per second, which is far from what we configured, the value of 10 gigabits per second. And this is because of the TCP send and receive buffers are not properly configured. Then we will show how we can modify them in Linux. So we will see this command, and I will explain it as we go through the lab. And later on, we run a test, the same test we run again, and we will see that we will be able to get the maximum throughput, which is around 10 gigabits per second. So this includes the set of slides. I can now move on to the hands-on session. So again, we are doing lab number 8. I already made the reservation. If you haven't done so, please just use the link in the website next to the session number 2. And then make sure to click on lab number 8, bandwidth, delay product, and TCP buffer size. All right, so like the other labs,
do you want to wait for maybe 1 or 2 minutes to give time?
Yeah, definitely.
Everyone.
Definitely.
So you're going to go through this lab number 8, which is the bandwidth delay product, but you will be explaining much more than BDP, right?
Yes, I will be explaining iPerf, how to emulate the wide area network, so how we can emulate delay, setting the speed of the link, and other commands as well.
And all these labs, I mean, there are, for the lack of time, we will not go into much detail. Eli will not go into much detail in for example, NETEM, which has several parameters, or the token bucket filter. All these are tools that are provided by Linux. But those tools are described in several other labs, like lab number 3 or 4 is NETEM, lab number 5 is token bucket filter, etc. So if you want to get more information about these tools, they are all available in the different labs. Yeah, I think we can proceed, Ali.
All right. Okay, so what you can see here now is on the left-hand side, I have a manual, and on the right-hand side, I have the machine. So in this series, we are only using one virtual machine. So if I go here to the pod, you will see that we only have client 1. And this is basically the machine that I'm showing on the right-hand side. But inside that machine, we will be emulating the whole network instead of having multiple machines here in the pod. All right, so so the lab start with first a table of content just to show the different sections. At the beginning of each lab, we have an overview, the learning outcomes, the objectives of the lab. We have a table that describes the credentials of the machine. For this machine, we have the username admin and the password, all small caps. And we will be basically using those as we perform some commands that require higher privilege. Then we have the introduction, which discusses basically the theory behind all the topics that we will do in the hands-on. And you can see here, we are talking about TCP buffers, bandwidth delay product, the observations when setting the TCP buffer size in Linux, and other topics as well. So if you want to go in details to understand the idea behind all the practical topics later on, you can read this introduction. It will give you enough background to go over the lab. So starting from section 2, this is where the hands-on starts. And this is the topology that we will be using. So we have 2 switches, 2 end hosts, and we will be emulating those in Mininet. So the first step is to start.
Eli, can I interrupt you for a second? So
Sure.
Christopher has a good observation. He said, my learning area just has workshop on networking topics dash perfSONAR. So do you wanna, or Jose, if you're there, do you wanna show how to access to the network tools and protocols labs?
Sure. I will post the enrollment link in the chat. And you can click on that. And if you are already enrolled into the persona, it's just a matter of clicking on this link and it will be added to your course and to your course list in the next login.
Okay, so yeah, Chris, you have Jose just shared the URL. Just click there and you will have access to the 8 to 10 lab, or actually 20 labs probably. And Elise going through lab number 8 right now. Apologize, Ali.
No problem. Shall I proceed or shall I wait a little bit so that everyone makes the reservation? And
Yeah, let's wait 1 minute. Perhaps there are some that are.
Sure.
So Brian, this is just the topology. Ali, I don't know if you shared your topology. It's just one client. Probably is a good idea. I don't know if this will derail you, but if possible, you can show from the beginning when you start in a different browser, maybe.
Yes, sure.
And also we will share with the Bill. I will share here the full lab series PDF. Again, Bill, I will share with you in a second.
So I'm using the link that is available on the website next to the hands-on session 2 enroll. And this should take you to the NDG portal. Okay, so once you are there, you should log in using your credentials. And from there, you will see the list of courses that you are enrolled in. So in this case, we are going over the NTP, Network Tools and Protocol. So I will click on that. And here you will see the list of labs from lab 1 to lab 20. In this hands-on session, we are going over lab number 8, which is bandwidth delay product and TCP buffer size. So you click on that. And basically what you would see here is the pod. This is available. So you can start now by running the experiment. You click on the client 1, and now you are inside the machine. Okay. And the content can be seen here in the content button. So what you can do is, as I was doing, you can open it in a new window, put it aside, and then basically put the other window which contains the machine on the right-hand side. This way you can follow both pretty easily. Is there any question regarding accessing the platform?
I think we're good, Ali.
All right, thank you. So basically, we talked that the first part is just the theoretical background. We are now in part number 2, which is the lab topology. So I will first start by clicking on the client 1 to enter to the VM. And from here, I will go over step 1, which is basically launching MiniEdit. Again, MiniEdit is the graphical user interface to edit the MiniNet topology. And there's an icon on the desktop that you can double click on it. And it's asking us for a password. So the password here is password all small caps. Okay, so once you type in the password, you hit enter, you should see the MiniEdit screen. Now here, where I was telling you that you can basically drag and drop these devices and create a custom topology. But to make things easier for us, we already created the topologies for each lab. And what we're gonna do now is open the topology that we already created. This is step number 2. And to do so, we have to go to File, then open, and then select the lab number. So file, open, and we are going over lab number 8 now. So I'll click lab number 8 and then click on open. And we can see now we have 2 switches and 2 end hosts loaded in our topology. And this is the topology that we were talking about using, right? So we will have 2 switches, 2 end hosts, and next we're going to be running the throughput test and all the other kinds of tests, basically. Now, at this time, we just loaded the topology that we want to run, but the topology hasn't started yet. And to start this topology, we have to click on the run button, which is at the bottom left of the screen. Once we click on the run button, the icons here should be grayed out, which means that the topology started. So now we can no longer use or drag any of these devices in our topology. As a quick reminder, so the topology uses 10.0.0.0/8. This is by default assigned by Mininet, and therefore host H1 will have 10.0.0.1 and host H2 will have 10.0.0.2. All right, so now we have our topology started. We can start by going over the end hosts and see what we can do there in their terminals. So the first step is to start the terminal of host H1. So step number 1 is to start it. The way to do so is we have to right click on the host H1 and we have to hold the right click. So make sure to hold it, otherwise the pop-up list will disappear. So click on it, right click on it and hold the right click and then select terminal. And you can see here that we have now a terminal dedicated for host H1. And here you can issue basically all kinds of commands that you have on your machine. So you can use ifconfig, for example. You can use ping, you can use traceroute, any kind of command that you use on Linux, you can use it now in this terminal. And the command that you write will be issued from host H1. Okay. If I want to give an example, I can type in ifconfig, and you can see I have the information about the interfaces that we have. So the interface name is H1ETH0, and this is the IP address that is assigned to that interface. So I will apply now the same steps to open the terminal of host H2, which is basically right-clicking on host H2 and then selecting terminal. So now we have a terminal for host H2 and another terminal for host H1. You can retrieve back those terminals. You will find them here in the start bar. So you can select H1, and now you are in H1, and you can shift between the two to select which device you want to perform the command from. The first step is to just try to see if we have connectivity between the two devices, and we will use the ping command to do so. So we are in step number 3. We're going to try to ping from host H1 to host H2. And we know that host H2 has the IP address 10.0.0.2. So I will start by typing in ping 10.0.0.2, and I will hit enter. And we can see that we have some replies from host H2, which means that we have successful connectivity between the two devices. To stop the test, you can simply press on Control-C. And at this point, now we are sure that the topology started well. We have connectivity, we have IP addresses assigned. Next, we can proceed to emulating the link speed and the delay that we want to introduce to our network. This is going to be done in section 2.2. So now we're going to start by assigning some parameters to the link, for example, setting the link speed or the bandwidth, and also introducing delay. And to do so, we want to make sure not to issue the commands from the terminals of host H1 and H2, because we are dealing now with switch S1 interface, which is here on the right-hand side, right? So we want to make sure to configure the network parameters on this interface. And to do so, we have to go to the terminal of the whole VM and not to the terminal of host H1 or host H2. So if you click on the show desktop button here, this is gonna minimize everything. And you will see that you have a terminal icon on the desktop. Okay. And again, this is the terminal for the whole VM that we're using. So I double click on it, and now we are inside the terminal. And again, here, this is a regular Linux terminal, so you can issue any command. What we're gonna be using is a tool called TC, which stands for traffic control. And this tool will allow us to basically emulate some conditions for a certain interface. So the first step is to introduce some latency, and we're gonna be introducing 20 millisecond delay. Therefore, we will have, after we issue this command, we will have a round trip time of 20 milliseconds. So the command that we're gonna type is this one. So I will explain as I go over it. So sudo for issuing the command with higher privilege. TC, this is the traffic control tool. QDisc, which stands for queuing discipline. So we are assigning these different kinds of queuing disciplines for a certain interface. And then we want to specify that we want to add to the device, so add dev, and then the interface name. So just to be clear, we have here S1-ETH2, and we are talking here in this interface about S1's interface facing S2. So we are basically emulating the latency here at S1's interface facing S2. Okay. So add dev S1-ETH2. And then we want to create a root handle so that basically once we emulate the delay, we will be able to also use that same handle to emulate other things, such as basically configuring the link bandwidth. So I will give it root here, and I will give it a handle. And again, this root handle will be used later on when I want to add another queuing discipline to that same interface. Okay. So now we have to specify what kind of discipline we want to add. So our goal here is to introduce some delay. And there is a very nice tool in Linux called NETEM, Network Emulator. It allows you to emulate different kinds of conditions such as packet loss, delay, packet corruption, packet reordering, jitter. It's very flexible. You can basically do a lot of configuration so that your emulated network can match as close as possible to a certain production network. In our case, we're gonna be using here just the delay. So I will write netem delay, and I will give it a value. In our case, we are emulating 20 milliseconds. So I will type in 20 ms. Now, in case you want to add packet losses, then all you have to do is space loss, and then you add the percentage of packet loss, right? And there's like a large list of conditions that you can emulate, but for now we are just using the delay. I press on enter, and it's asking me again for the password. The password here is password all small caps. All right, so at this point now, we emulated the delay on the interface. What we're gonna do next is modify the bandwidth of the link that is connecting switches S1 and S2, and we're gonna set it to 10 gigabits per second. Now, to change the bandwidth of a certain link, we can use a queuing discipline that is called TBF. TBF stands for token bucket filter. And it's a very well-known classic way of basically specifying a certain rate. You have to give it some parameters, such as what is the rate that you want to configure. In our case, 10 gig. There's a parameter called burst that you have to configure it as well. So how can we get this value? Basically, this is discussed in lab number 5, but basically, a good rule of thumb is just to divide the rate that you want to configure by the clock rate in your system. This is gonna give you around 5 megabytes. And then you have the limit, which is basically how big your buffer size is. Okay. In our case here, we are setting it to 25 megabyte. All right. And we start by typing this command in the same terminal. So sudo tc qdisk. Notice how so far it's all the same. Add for the same interface s1-eth2. But now what we're gonna do is we're not gonna create a root one. We're gonna instruct tc to attach this tbf to the already created NETEM there. And we know that we created NETEM with the handle 1, so we have to tell it now, use parent 1. Again, this one here corresponds to the handle that we created. And give it a new handle for this tbf, which is 2. So again, we are just creating this tbf now, and we are attaching it to the same queuing discipline that we used before, which is NETEM delay 20 milliseconds. Okay. Next, we have to start by specifying what is the queuing discipline. In our case, it's tbf, token bucket filter, and the parameters for tbf. So we have the rate. We want it to be 10 gigabit. So 10 gbit. You can also specify in megabit. And then the burst size, which is 5 million. And finally, the buffer size, which is indicated here with the keyword limit. And this is 25 megabyte. And I hit on enter. Okay. So what we've done so far, we configured the interface S1-ETH2, which is the interface of the switch S1 facing S2, to have 20 millisecond delay. So we are emulating 20 millisecond delay, and we are setting the rate to be 10 gigabits per second. We also specified the buffer size for that interface. Now we're gonna proceed and test some of the configuration that we've done. So first, we're gonna run the same ping test that we did in the at the beginning of the lab, and this is gonna be executed on the terminal of host H1. So make sure to open the terminal of host H1. Again, you can select it here, so it will show you specifically host H1, host H2. So I will go to host H1 and type in again ping 10.0.0.2, and then I will hit enter. And you can see how now the round trip time is 20 milliseconds. And basically also you can see previously it was very small, and now we were able to successfully introduce or emulate this 20 millisecond of round trip time. Okay. I will press Control-C to stop the test. And we can proceed now to test the throughput. And we know that ping is used for latency. We can use iPerf3 to test the throughput now. And this is step number 4. So remember that we talked about iPerf3. This is a client-server application. So before we start testing the throughput, we want to make sure that the server is listening for incoming iPerf3 clients. Okay. And in our scenario, I'll go back to the topology. What we're going to do is we're going to set host H2 as the server and host H1 as the client. So host H1 will be sending data to host H2. Okay. To make host H2 as an iPerf3 server, we have to go to the terminal of host H2. So again, make sure to select host H2. And there I will start iPerf3 in server mode. For those of you that are receiving this pop-up, which means that the reservation might end soon, you can simply press on request more time, and this is gonna extend your reservation. Okay, so let us start now iPerf3 server on host H2. I will type iPerf3-s, -s for server. And now we're gonna start iPerf3 in client mode, but now we're gonna do it on host H1. So this is step number 5. We have to go back to the terminal of host H1. And from there, type in the command iperf3 -c, and then the IP address of the iperf3 server, which is the IP of host H2 10.0.0.2. And I will hit enter. And by default, iperf3 will run a test for 10 seconds, and it's showing us the bitrate for every 1 second interval, and also it's showing the amount of bytes sent. So what we should get from this output is that we are achieving on average a throughput of 2.6 gigabits per second. But we tried to configure the interface to 10 gigabits per second. And there's a reason why we are reaching this throughput and not the 10 gigabits throughput. Okay. And the reason is the TCP buffers are not properly tuned. So we want to make sure to tune them well and then repeat the test and see if we can get high throughput. Okay. iperf3 can be used for a lot of other tests as well. So we can use it in UDP mode, TCP, and maybe we can start multiple servers and run more complex tests. But the goal here is just to show you that if you just out of the box have a 10 gig link, when you don't do any tuning to the end hosts, you won't be able to get the full throughput. You have to perform some changes. And what is important to know is that the changes that we're going to describe next are exactly the same thing as you would do in a real server. So we are not only talking about MiniNet emulated device. These are the same configurations that you have to do on servers that you just use in your network. Okay. So moving on now to section 3, which is the BDP and the buffer size. So this is where we're going to see how we can inspect the send and receive buffers that are being used by TCP. And we will see how also we can modify them. So in Linux, there's the sysctl tool, which many of you might already be familiar with because it's used to basically tune many of the kernel parameters, not only TCP specific or data transfer specific. So there are some parameters that you can change using this sysctl tool. One of them is the TCP receiver window size or TCP buffer, and also the send buffer. And they have different keys basically. So let us start with step number 1, which is to see what is the currently configured value for those window sizes on host H1 and on host H2. So first we will start with host H1. We are there. This is the terminal. I can type in sysctl. So I'm typing in now this command here. sysctl net.ipv4.tcp_rmem. And this is going to show us 3 values. So we have the minimum. That's the first one. We have the default and we have the maximum. And those are represented in bytes. And we can see here that the maximum buffer, TCP buffer that is configured is around 16 megabyte, which is lower than our bandwidth delay product. And this is kind of telling us why we can't really achieve this 10 gigabit. Now, same thing you can do to check now the send buffer, which is exactly similar, but instead of using RMEM, you use WMEM. And we can see here also these are the same values. And by the way, the values that you see here are the default ones in Linux, at least in this distribution in Ubuntu, right? So if you are using this out of the box, that's the currently configured buffer size, and you need to make sure to modify it. All right. Now, we talked about our bandwidth delay product. So we have 10 gig link, right? We configured a link of 10 gigabits per second, and we have an emulated round trip time of 20 milliseconds. And so if we do the math, so if we just multiply these two quantities, we will get the bandwidth delay product. So it's 10 gig multiplied by 20 milliseconds. And the bandwidth delay product is around 25 megabytes. Okay, so we want to make sure to configure our buffers to a value larger than this so that we can attain the full throughput. Okay, now we talked a little bit about this in the slides, but I'm going to repeat it again. In Linux, by default, whatever value that you specify here for these buffers, only half of it will be used for your applications. The other half will be used for other internal structures. So if you want to use 1 BDP, you have to make sure to multiply it by 2, right? So you would eventually set 2 BDP here. Okay, and then the Linux will be using half of it, which is 1 BDP, and this is going to be used for your application. So 1 BDP is around 26 megabyte, and then 2 BDP is around 52 megabytes. So we will configure the send and receive windows to have a maximum value of 52 megabytes. How can we do this? We have to use also the sysctl tool, but now we have to give it the -w, which means that we want to write some value to a certain field. And then you give it the key, which is net.ipv4.tcp rmem equal, and then the value. So sysctl works in a key value approach. So the key is here in this case, the TCP rmem, and the value is whatever you write after the equal. So we're going to keep the minimum and the default as they are, which is 10.240, and then space 87.380. And now we're going to change the maximum to be around 52 megabytes. So 5242880. You don't necessarily have to have it exactly that. So if you type in basically 50 million, it should do the work, right? But we are just showing how when you do the calculation, you'll be able to determine that value to be placed there. Now, another important point is that many times you don't want to be repeating all of this again and again. So you need to have it persistent. And the way to do so, there's a file. I can open it here. It's in /etc sysctl.conf. Okay. And basically this file contains all the fields that you want to override. So if you want to decide to use this send and receive buffer at all time without having to reissue that command again and again, you can basically type in the key and the value pairs inside this file. This way, whenever you turn on your machine, it's going to read this file and then apply the configuration. Okay. All right, so we changed the receive window. Now we're going to do the same, but for the send window. And to save time, I will just use the up arrow. This is going to give me back the previous command that I wrote. And then, so we are basically here in step number 2. All we have to do is simply change the rmem to wmem and press enter. Okay. So now we changed the value of the send and receive window, the maximum value to 52 megabytes. Next, we will do the same thing, but on host H2. It's a good idea to always modify both sides of the session because maybe both sides are going to be transmitting data. And you want to make sure that both are not bottlenecked by the value of these send and receive windows. So to modify it on host H2, first we have to go to host H2. Click on host H2 here. We can see that the server, the iPerf3 server is still listening because by default, it will keep listening till you just explicitly stop it. I will use Control-C here to stop the iPerf3 server so that I can issue the sysctl commands. Okay, so let me type now the sysctl on the host H2. So net.ipv4.tcp rmem. Again, we're going to use the default values for the minimum and default. And then we have to use the 2 BDP here, in this case, to the maximum buffer. Okay, and same thing for the other parameter, which is the sending window. I will use the up arrow and change from RMEM to WMEM. Okay, so this is all we have to do to make sure that we are using large buffers. There are some observations that are mentioned in the lab. For example, if you are planning to use congestion control algorithms other than the default one, which is cubic, you might encounter some situation where you want to increase more of those send and receive buffers, especially in an algorithm called BBR. So there is some information in the lab. If you are interested, you can go over it more. But typically, setting it here to 1 BDP should be good for loss-based congestion control algorithms such as cubic, the default one we use in Linux systems. All right, so step number 5 is to proceed and start again our iPerf3 server so that we can repeat the test that we did before. So iPerf3-s, the server is listening. And now we can go to host H1 and restart our client, our iPerf3 client, to see the throughput that we get. So make sure to go to host H1 terminal. And there we will issue the command iPerf3-c 10.0.0.2, the IP address of host H2. Press on enter. And we can see now a very significant improvement in the throughput. So we are basically achieving the maximum theoretical bandwidth, which is close to the value that we set, 10 gigabits. So on average, it's around 9.37. That you can see at the beginning of the test, there was some losses. This is completely normal, just for TCP to adapt. And then we were able to fill the pipe, the BDP. We have the receive and the send buffers properly configured so that they can absorb this amount of traffic. And this is why we are now fully utilizing our link. So this is the end of this lab. The idea is just to show you that some really trivial tuning that you have to do on the end hosts are very important, and you will see significant improvement in your throughput. In this lab, we talked about the send and receive buffers, but there are other labs that talk about buffer size on the router. There are other labs that talk about congestion control and stuff like that. So it's a good idea to see all the remaining labs if you are interested, to make sure to tune your network properly.
Thank you, Lee. I think there are some observations, and I don't know if you want to address. Brian said, could you throw a -R on there and rerun, please? I'm getting much lower in reverse.
Yes, so let's try it first. Yeah, so we got around 7 gig. The thing that we should keep in mind with this kind of scenarios is that whatever you use on the TBF or NETEM or any of these emulators, they are applied to an interface basically depending on a certain direction. So if you want to maybe run it in the other direction, you have to make sure to apply it to switch S2 specifically on this interface here, and then it should basically work. There should be like some proper or more deeper explanation to this if we do the brainstorming, but I'm sure that if you run it in the other way and you modify it on S2, this should give you the full throughput.
Yeah, very quickly. I mean, without a deep analysis, the test that you did before from H1 to H2, prepare first the bottleneck link was 10 gig in that direction from S1 to S2, but also the buffer size that you set on S1 was large enough from that direction from S1 to S2. I'm guessing that you will have to establish enough buffer also if you do on the other direction.
Yeah, definitely. Yeah, there's a lot of tuning depending on the scenario, but the nice thing about Mininet is it's fairly easy to deploy complex topologies. And if you just try here to run an iPerf test without limiting the rate, you can get up to around 50 gigabits per second. So it's going to really give you a lot of flexibility in testing with high speed links. And as well with the combination of NETEM, you can emulate not only delay, but also like packet losses, and you can give the probability of a packet being dropped. So it can really give you like a characterization, if you know your network well, to reproduce that scenario and try to troubleshoot or try to see what you can improve there.
There's another comment or question. Can the emulation be model / hardware specific, or are the switches fairly generic in its emulation? I don't know if you want to address or you want me to address. Up to you.
I want to make sure that I understand the question correctly. So the commands that we're using now basically are available in hardware targets. So not the same commands basically, but you can, for example, modify the buffer size on some routers. You can modify the link speed and stuff like that. Now, the commands that we're using are purely emulation for these software switches. The one that we are using here are OVS, the Open Virtual Switch, and it's a Linux based, so all the Linux commands available for you there for emulation, you can apply it to them. You won't be able to apply, for example, TBF on the router itself, right? Or NETEM on the router, a physical router, but maybe you can apply it in some other devices along the way, or if they might have like other kind of emulators. I know that there are some physical emulators that can add latency or can change the bandwidth of the link.
I will add to what you said, and you didn't make emphasis on the buffer size, but the third parameter that you were configuring the switch S1 was the buffer size, and that is, for example, the idea is a general idea you are applying to your software switch, but still you see exact or similar effects that what you are able to see on a physical device. And on a physical device, you can also set the buffer size. So there are some ideas that translate directly from the software switch that it is using to the physical switch, some switches that allow you to do the buffer modification, and others that are a little bit more specific to the software switch. Okay, with this, we are finalizing the program of day one. Certainly, we have a few minutes for questions, discussion. I am sharing in the chat window. We would appreciate if you can give us the feedback for this day number one. It's going to be very useful, so we improve from here. And now I see another comment. In our example, for H1, H2 flow, only send window on H1 and receive on H2 needs to be configured. Eli, I don't know if you want to address that.
Yeah, basically that's correct. Unless if you want to do it like on different directions, you want to make sure to have them both configured.
And again, on the with that, I want to emphasize again, and we would appreciate if you can give us the feedback. Workshop day one survey. The survey is already in the chat window. with that, Jason, Christy, Jeff, I don't know if you want to share something else before we close this day number 1.
Just again, our thanks to everybody for sticking with us as we worked out some of the technical issues, and hopefully everybody got something out of today's presentations. And certainly if you think of questions between now and when we meet again on Tuesday, we're available to answer them. But otherwise, we're just happy that everybody can join us today, and we'll make sure that all the information gets posted, and we'll be ready to talk to everybody again in 1 week's time.